Alright, so in this question we are dealing with a initial value problem, and it's asking us to, well, solve the initial value problem, find the general solution, and all that, and then find the value of y of 2. So the first thing I'm going to point out before getting started with this problem is what you'll notice is that on the right side we have an x term on its own as well as we have this x term right here, and then we also have a term here in parentheses where the only variable is y. And so the fact that these two terms are separated from each other already is leading me to believe that this is going to be a separable differential equation. Not to mention that if it was a case where if you wanted to find a general solution using an integrating factor, then usually the equation would take up the form of an equation that can be solved using an integrating factor. So yeah, so it's safe to assume that this differential equation can be, a general solution of it can be found by using separation of variables. And so the first thing I'm going to do to show that is I'm going to rewrite this a little bit. So I'm going to rewrite this as y dy over dx is equal to x times y squared plus 1 over 1. And then I'm going to cross multiply, and that gives us y dy is equal to x times y squared plus 1 dx. And then from here, we can divide both sides by y squared plus 1, and we'll be able to successfully separate and isolate the y variables onto one side with respect to y, and have the x variables on the other side with respect to x. So when you divide both sides by y squared plus 1, you end up with y over y squared plus 1 dy is equal to x dx. And from here, the two variables have been separated successfully. And so from here, to find the general solution, all we have to do is integrate both sides. So we just attach an integral to both of these sides. And the right side, that's trivial. That's just x squared over 2. So this will go to x squared over 2. And then the left side, so this y term here, this can be solved by just using a u substitution. So saying that u is equal to y squared plus 1, and then du is equal to 2y dy, my bad, 2y dy. So then dy is going to be equal to du over 2y. And then plugging in our substitution values back in, we end up with the integral of y times du over u times 2y. And then these two y's are going to cancel, so you end up with the integral of just 1/2 u du. And then that just equals 1/2 times the natural log of the absolute value of u. And we know that u is y squared plus 1, so we can just put y squared plus 1 back into here. And so now we can finally complete this and say that 1 over, and that's, I wrote an n there, that's supposed to be a 2, my bad. So yeah, so then we can say that now we have, let me rewrite this down. So after integrating both sides, we end up with the term that takes up the form of 1/2 natural log of y squared plus 1 is equal to x squared over 2 plus some constant. And so all we have to do from here is we need to isolate y and have everything else on the other side. So the first thing I'm going to do is I'm going to multiply both sides by 2 because we have a 1/2 leading in front of both terms here. And so when you do that, you end up with the natural log of y squared plus 1 is equal to just x squared plus some constant. And the reason that I didn't multiply the constant times 2 is because that constant can be any constant. And if you were to go backwards and differentiate this again, that constant would just go to 0. And so when you multiply some constant times 2, it's still just going to be another constant. And so that's why I just left it as c instead of 2c. And be careful with that, because sometimes you can end up getting the wrong answer if you do that on a different question. So yeah. And so from here now, and then the next step I have to do, and then let me put an arrow here to show that I went to here. And then the next step we have to do is I want to get rid of this natural log. So I'm going to attach an e term. So you end up with, canceling out the natural log, you end up with y squared plus 1 is equal to e to the x squared plus some constant. And then this constant can be moved out of the exponent side, and you end up with just y squared plus 1 is equal to some constant times e to the x squared plus 1. And then the next thing from here, all we have to do is we have to move this 1 to the other side and take a square root to get, we move this 1 this one to the other side and take a square root to get rid of this exponent over here. And when you do that, you ultimately end up with a general solution that takes the form of y is equal to the square root of c times e to the x squared minus 1. And from here, now we can solve our initial value problem. So zooming out a little bit, we end up with, we know that y of 0 is equal to 1, so all we have to do is plug in 0 for x and 1 for y, and we'll be able to solve for the constants. So moving this up here, we end up with 1 is equal to the square root of c, just c, because it's e to the 0, so c minus 1. And then squaring both sides, we end up with 1 is equal to c minus 1, and then c is ultimately going to be equal to 2. And so now that we solved the initial value problem, the solution to this initial value problem is going to be equal to y is equal to 2 times e to the x squared minus 1 in a square root. And from here, we can solve the last part of the question, which is asking us to find what y of 2 is. And so y of 2, that's just plugging in 2 for x, so we can say that y of 2 is equal to 2 times e to the 2 squared, which is 4, minus 1. And then this is going to be our final answer. And so matching that up with the answer choices here, you should end up with C. Oh, oops. We should end up with C. And hopefully, if I didn't do anything wrong, yeah, okay, yeah. So the answer to this question is going to be C. All right, so what is the largest open interval in which the solution of the initial value problem is guaranteed to exist by the existence and uniqueness theorem? So this is a question where we're checking to see where there would be a situation where the solution would be undefined depending on what t is in this equation given to us here. Because there are situations where depending on what t is, you could end up with a situation where you could have an undefined answer. And I'll show you how. So the first thing I'm going to mention is here, notice here we have a fraction here. So this 2 over t minus 10. In that case, when t is equal to 10, you'd have a discontinuity there, because when t is equal to 10, then that would simplify to 2 over 0, and you can't divide by 0, so that would be a discontinuity. And so to start, the first thing I'm going to do to find all of those situations where there could be a potential discontinuity is you want to divide everything, you want to isolate the y prime. So to do that, I'm going to divide this by this entire equation by t minus 3. And so when you do that, you end up with y prime plus the square root of t minus 1 over 6 divided by t minus 3 times y is equal to 2 over t minus 10 divided by t minus 3. And then you can further simplify this down to y prime plus the square root of t minus 1 over 6 times t minus 3 times y is equal to 2 over t minus 10 times t minus 3. And so now we have all the terms that we want in the denominator that will help us to see where the discontinuities are. So in this case, we have two potential situations that would give us a discontinuity, that being this t minus 3 term here and this t minus 10 term here. And so we know that we can set up a couple of equations to find those situations. So we can say that t minus 3 is equal to 0 and t minus 10 is equal to 0. And when you solve these equations, you end up with t is equal to 3 and t is equal to 10. And so that tells us that there's going to be an undefined answer to the solution when t is equal to 3 and when t is equal to 10. Because when t is equal to 3 and when t is equal to 10, that's where you end up with a divide by 0 situation. And we can't do that. So the next thing I'm going to do is I'm going to put down a number line here, because the next thing we have to do is we need to compare those points where there's an undefined answer or a discontinuity relative to the initial condition given to us, that being this, where our initial condition is equal to y of 5 is equal to 2. So let me write that down here. We were given the initial condition that y of 5 is equal to 2. So on the number line, I'm going to put in the middle, I'm going to say that t is equal to 5. And the largest open interval is that we need to find the largest open interval between discontinuities relative to the initial condition, because it's in the name. So we have the name says It says existence and uniqueness. So existence being a solution exists, and uniqueness being based on the unique initial condition given to us here. And so as a result, we know that the solution is going to be undefined when t is equal to 3 and when t is equal to 10. So I'm going to put points here. So t is equal to 3 here, and t is equal to 10 here. And basically we know that everywhere else the solution is defined. And so as a result, we can say that there's an interval of where a solution is guaranteed to exist between t is equal to 3 and t is equal to 10. Now, the reason why this is going, then so as a result, this is going to be our largest interval. Now, you might be thinking, there are other places where there's an interval where the solution is guaranteed to exist. So, for example, like beyond 10, technically speaking, yes, you can say that beyond 10, all the way to infinity, then yes, that's also an infinite interval where a solution is guaranteed to exist. And then you can also say that there's an interval here going to negative infinity. So from t to negative infinity. The reason why those intervals are not valid is because those intervals are not connected to our initial condition given to us here. And so as a result, we know that, but we know that the interval from 3 to 10, we know that that interval crosses over the initial condition given to us. And so as a result, that ends up being the largest open interval where a solution is guaranteed to exist. And so so the answer to this question is going to be B. So in this question we are dealing with a Wronskian matrix, and a given function f of t is equal to t of 2, where t is greater than 0, and it's asking us to figure out what the other function was for this Wronskian matrix that gave us the answer of 4t to the 4th. So to start, recall that with a Wronskian, we know that w of f of g is equal to, well, that's a little messy, let me rewrite that. So we know that for a Wronskian, in this case w of f of g, that is equal to the determinant of f of t, and then g of t, and then the derivatives of those two functions, because the Wronskian is always going to be a square matrix that involves the functions and its derivatives. So since we have two functions, we're gonna have a 2x2 square matrix with just one derivative. And then if you, for example, like if you had three functions, then you'd have a 3x3 matrix, and you'd be including the first derivatives as well as the second derivatives of those functions, so that you could end up with a 3x3 matrix. So for this case, yeah, the determinant is going to be a 2x2 matrix. So f of t, f prime of, okay, my computer is bugging out again. Okay, there we go. So yeah, so f prime of t, and then g prime of t, and then we take the determinant of that, and that would be equal to 4t to the 4th. So to start, we know what one of the functions is, that being f of t. So I'm going to say that f of t is equal to t squared. So the derivative of that would just be f prime of t is equal to 2t. And from here, all we have to do is we need to find what g of t is. We have everything we need to do that. So I'm going to set up the determinant. So we know that the Wronskian, so w, f, and g is equal to the determinant of t squared and then 2t, and then g of t, and then g prime of t. Since we're taking the determinant of a 2x2 matrix, that's going to be equal to the top left times the bottom right minus the bottom left times the top right. So that gives us a equation that takes the form of t squared times g prime of t minus 2t times g of t is going to be equal to 4t to the 4th, because we know that this Wronskian is equal to 4t to the 4th ultimately. We just have to find what g of t is. And so from here, the next thing I'm going to do is I'm going to divide this entire equation by t squared. And when we do that, we're going to end up with an equation that takes the form of a differential equation where the general solution of that can be found using an integrating factor. So this Wronskian question in reality is actually just an integrating factor question disguised as something else. So when you do that, you end up with g prime of t minus 2t over t squared times g of t is going to be equal to 4t to the fourth over t squared. Simplifying this down, the next thing I'm going to do is I'm going to rewrite the, actually, yeah, so actually no. Yeah, to simplify this, you end up with just g prime of t. Let me also, let me move things around a little bit so make things a little neater. So I'm actually going to rewrite this over here, so we end up with like this. Dividing the entire thing by t squared, we end up with g prime of t minus 2t times g of t over t squared is equal to 4t to the fourth over t squared. And then when we simplify this, we end up with g prime of t minus 2 over t times g is equal to just 4t squared. So from here, you can probably more clearly see that in order to find a general solution to this differential equation, we'd have to use an integrating factor, because recall that when you see an equation that takes the form of, like, in this case, we have g, so dg dt plus p of t times g is equal to q of t. We can clearly see that q of t is equal to 4t squared here, and we can clearly see that p of t is equal to negative 2 over t, and then dg dt, that's just g prime of t. And so yeah, so all we have to do from here is come up with our integrating factor and then distribute that integrating factor into the entire equation, and that will allow us to integrate both sides, giving us a general solution. So recall that to find an integrating factor, I'm going to denote that as rho. So rho of t is going to be equal to e times the integral of p of t. And we know that the p of t function is going to be negative 2 over t. So rho of t is going to be equal to e to the integral of negative 2 over t. And that's going to be equal to e to the negative 2 ln of t. And from here, we can simplify this a little bit, and this will ultimately simplify to rho of t is going to be equal to 1 over t squared, because we have an e term here and we have a natural log here, so they're inverses of each other, so the e and the natural log are going to cancel. So actually, yeah, let me write it out. So this would be equal to 1 over e to the 2 natural log of t. And then from there, you can see how the natural log and the e cancels, and we end up with this term over here. So our integrating factor is ultimately going to be equal to rho of t is equal to 1 over t squared. So the next thing we have to do is we need to distribute that with our differential equation. And so when we do that, we end up with 1 over t squared times g prime of t is, or minus 2t over, no, my bad. Minus 2 over t times 1 over t squared. That just simplifies to minus 2 over t cubed times g, or g of t, is going to be equal to 4 t squared, so 4t squared over t squared, which just simplifies to 4. So our final differential equation with the integrating factor included is going to be 1 over t squared g prime of t minus 2 over t cubed g of t is equal to 4. And then all we have to do from here is we need to integrate both sides. So let me give myself a little bit of space. And so when we do that, you should end up with an equation that looks like the integral of 1 over t squared times g prime of t minus 2 over t cubed times g of t dt is equal to the integral of 4 dt. And so the right side, that's trivial. That's just you're just integrating a constant, so that's going to be equal to 4 over t. So this is going to evaluate to 4 over t. And then the left side is also really easy. If you don't remember, when you're finding a general solution using an integrating factor, the reason we want to use an integrating factor is when you distribute that integrating factor into the left side, you end up setting it up in such a way where the left side of the equation, let me rewrite it as this. So this left side of the equation takes the form of, we have our integrating factor, so rho of t times g prime of t minus this term here. And what you'll notice here is that when you multiply your integrating factor with the pt equation, the p of t term that we had over here, you're going to find that actually takes the form of the derivative of the integrating factor. So this left side of the equation ends up just taking the form of rho prime of t times g of t, because we know that the derivative of 1 over t squared, that's just negative 2 over t cubed. And so what you'll notice here is that the left side just takes the form of like some derivative that was found using the derivative product rule. And so the computation for integrating the left side is just as simple as going backwards. And so you know that the product rule for a derivative, we know that the product rules, I'm going to use rho and g since those are the functions we're dealing with. So d dt of rho of t times g of t. We know that that's using the product rule, that's equal to rho prime of t g of t plus rho of t times g prime of t. And so finding this integral is just going backwards. And so the left side is just going to be equal to rho of t times g of t. So our final solution is we're going to end up with the final equation that takes the form of 1 over t squared times g of t is going to be equal to 4t plus some constant. And from here, all we have to do is solve for g of t, and we have our answer. We basically have because the answer is just going to be the general solution to this differential equation. And so when we do that, I'm going to move this 1 over t squared to the other side to cancel it out with this to isolate g of t. And we end up with g of t is going to be equal to 4t cubed plus ct squared. And so yeah, we have found what g of t is equal to. And if you're not sure, you can if you have a little bit of time. I know this is for an exam, so you probably won't have time. But if you're not convinced, you can plug in the g of t that we found back into the matrix to find the Wronskian. And when you plug in the g of t and the derivative of g of t and take the determinant, you will in fact end up with 4t to the fourth. And so yeah, so we have our final answer over here. And so comparing that with the answer choices over here, it looks like the constant is just on the other side. So the answer that matches up closest to our answer would be E. So the answer would be E for this question. Okay, so in this question, we are given a tank of total volume 200 liters, which initially contains 100 liters of pure water. A brine solution of concentration 0.2 kilograms per liter is pumped into the tank at a rate of 10 liters per second, and the well-mixed solution in the tank is pumped out at a rate of 7 liters per second. So write the initial value problem for the amount of salt x of t in kilograms at time t in seconds before the tank overflows. Okay, so in this question, we're dealing with a mixture problem, good old salt tank questions. So for the first thing I'm going to do is I'm going to model our system so that we can kind of visualize it a little bit better. So to start, we know that we're given a tank. So just a tank over here. Let's say that, and that tank has a total volume of 200 liters, and but it initially contains 100 liters of pure water. I'm going to put more emphasis on this volume because that's going to be more important. So we know that this tank, it has 100 liters of pure water initially. And then it tells us that a brine solution of concentration 0.2 kilograms per liter is pumped into the tank at a rate of 10 liters per second. So we can say that some solution over here is being poured into the tank. I'll just use, I guess I'll use purple for that. Or no, I'll use red for that. It's going into the tank like this. And then it also tells us that a well-mixed solution, so the brine solution mixed with the pure water, is being pumped out at a certain rate. So that's being pumped out. So we can just say that it's coming out of the tank like this. We can just say that there's a hole in the bottom of the tank, and the well-mixed solution is coming out like this, like that. And so now what we have to do is we need to work with some of the values that were given to us, and come up with an equation that we can work with. And so we know that for questions like this, we can model a differential equation that takes the form of dx dt. So actually, no, let me write that down here. So we can write a model differential equation that takes the form of dx dt is equal to the rate in times the concentration in minus the rate out times the concentration out. That's supposed to be a C, not an R. And then usually for questions like this, they usually give us some of the values beforehand as well. So we know that the rate in is given to us in this form, where it tells us that a brine solution of concentration 0.2 kilograms is pumped in a liter at a tank of 10 liters per second, like so. So that tells us that our rate in is going to be equal to 10 liters per second, and our concentration in is going to be 0.2 kilograms per liter. And so we have two of those things taken care of. And then it also tells us what the rate out of the well-mixed solution is going to be. So the rate out that we're given, it's being pumped out at a rate of 7 liters per second. So we can say that our rate out is going to be equal to -7, liters per second. And the reason why it's negative is because it's leaving the tank rather than being added to the tank. So it's like a subtraction. And so now all we have to figure out is what our concentration out is going to be, because it's going to be different from, oops, get rid of that. It's going to be different from the concentration in, because the concentration in, well, that's constant. It's given to us as 0.2 kilograms per liter, but the concentration out, that's different because now we have a well-mixed solution that includes both the brine solution as well as the pure water. And so we have to say that the concentration out, that's not supposed to be a 7, by the way. This is supposed to be a question mark, but my computer was acting up, so let me rewrite that. So yeah, so now we have to figure out what our concentration out is going to be. And once we have that, then we can complete our differential equation. So recall that with concentration, we know that concentration is going to be, that's equal to the amount of whatever thing we have. So that's going to be equal to the amount, in this case, whatever the thing in question we're dealing with is salt. So the amount of that good old sodium chloride over the total volume of the, I guess, of the total system. And so let's just say total volume. And so then, and then also I'll write salt so I don't confuse anybody. So let's just say the amount of salt. And then the total volume. And so the total volume, that's going to be, so for the total volume, since this is the concentration out, so the concentration of the well-mixed solution, the total volume, we need to account for the initial volume as well as the rate in and the rate out. And so we can say that the total volume, that's going to be equal to our initial volume, so VI, plus our net rate, so R in minus R out times T, because the rate is that's a time-based value, and so that's why I have a T attached here. And so we know that our initial volume, I mentioned how I was going to be focusing on this 100 liters value here because that's what matters here. This 200 liters, this doesn't really matter to us in this question. It's kind of pointless information. So let's just ignore that for now. So I'm gonna gray that out because it doesn't tell us it doesn't mean anything for us here. It would mean something later on for, like, if the question was asked for, I guess, a couple of other things, but for this question it doesn't mean anything to us. It's useless information. So we know that but what matters to us is the fact that we know that there's 100 liters of pure water. So that's going to be our initial volume. So our initial volume, I'll write that over here as well. VI is equal to 100 liters. So our total volume, that's going to be equal to 100 plus the rate in minus the rate out. So our rate in is 10 liters per second, as we've put here, and our rate out is negative 7 liters per second. So 10 minus 7, that gives us 3. So our total volume is going to be equal to our net rate is going to be 3T, and this is going to be our total volume. Now for the amount of salt, we know that in the general form of the differential equation that I've written here, we know that dx dt, that's equal to the amount of salt at any given time. That means that x is going to be our variable that represents salt. It also tells us in the problem to use x for that too as well. So we can say that our amount of salt, that's just going to be equal to x as a result. And so now that we have all the things that we need, we can finally narrow this down, and we can say that C out, the concentration out, is going to be equal to x over the total volume of 100 plus 3T. And now we have everything we need here. So let me organize this a little bit. So getting rid of this and getting rid of this question mark, we can say that our concentration out is going to be equal to 100 plus 3T. I'll put the volume back up here, and V initial, that's just 100. Sorry about that again. My computer is not being nice to me today. Okay, there we go. Nice. So now that we have all the values we need, we can plug that into our differential equation and proceed further. So putting this down here, we can say that dx dt, that's going to be, we're plugging in our values, we end up with 10 times 0.2 minus the rate out of 7 times the concentration out of x over 100 plus 3t. Simplifying this down a little bit, we end up with dx dt is going to be equal to 2 minus 7x over 100 plus 3t. And this is going to be the final form of our differential equation for this question. And so from here, we can start to eliminate a couple answers. So we can get rid of a, b, and c. So a, b, and c are automatically out of the question because the differential equation in those answer choices does not match our choice. Now it's just a matter of figuring out what our initial condition is going to be. So it's down to d and e. And so for that, it's telling us to write an initial value problem of the amount of salt at time t. And so, and since it's an initial value problem, we have to come up with an initial condition. So the initial condition, we can say that that's like what's going on when t is equal to 0. So let me write that down. So let me write that down over. Let me write that down over here. So okay, there we go. What's happening when t is equal to 0? That's going to be our initial condition. So we can say that x of 0, what's going on then? And for that, we know that since x is the amount of salt, that's the amount of salt in the solution at a given time t, we know that we're initially dealing with 100 liters of pure water. It tells us pure water over here. That means that there's no salt in the tank initially. So we can say that when x is equal to 0, there's no salt in the tank, so we can say that x of 0 is going to be equal to 0. So our final initial value problem is going to take the form of this differential equation like this, and an initial condition saying that x of 0 is going to be equal to 0. So this is going to be our final answer for this question, and we can get rid of e as well, because it tells us that in this initial condition, it tells us that x of 0 is equal to 100. That means that there's 100 kilograms of water in the tank initially, which is not true because it tells us that we have 100 liters of pure water. So as a result, all that leaves us with is an answer of D. All right, so in this question, we're dealing with a autonomous differential equation, and it's asking us to decipher which of the critical points of the autonomous equation are going to be stable. So recall that with an autonomous equation, the autonomous equations are going to have critical points, and those critical points can either be one of three things. So they can either be stable, semi-stable, or they can be unstable. So with that out of the way, I'm going to revisit those points later. The first thing we want to do is we want to find the critical points, obviously. So in order to do that, set the autonomous equation equal to 0 and then solve for x. And so the next thing I'm going to do to make this a little bit easier to see what the critical points are, I'm going to split up the given equation in a way that makes it more obvious. So dx dt would be equal to x times x plus 1 times x plus 1 times x minus 3 times x plus 2 times x minus 2 is equal to 0. After splitting it up this way, you can more clearly see that the critical points we're going to end up with is x is going to be equal to 0, negative 1, negative, oops, let's get rid of that. 0, negative 1, negative 1, 3, negative 2, and 2. And then since we have a duplicate here, we can just condense this into a single critical point. And so ultimately we end up with the 5 critical points. So 0, negative 1, 3, negative 2, and 2. And the next thing I'm going to do is I'm going to plot these critical points onto a number line. So let's just put that here. So I'm going to put a number line over here and plot the critical points in ascending order, starting from negative 2 to negative 1, 0, 2, and 3. So the next thing we have to do from here is we need to analyze the way the function or the autonomous equation is going to behave around each critical point. So rather than exactly what the critical point is, we'd have to look at numbers that are slightly below the critical point and slightly above the critical point. And that's going to tell us whether that point is a stable or unstable point. So I'm going to start with the lowest number. So since our lowest critical point is negative 2, let's just say x is equal to negative 3. Now the next thing you want to do is you want to plug in your test number back into your original autonomous equation. I'm going to be using the split up version of it because I feel like it'll be easier to figure out whether or not the answer we end up with is negative. Because what we have to do is, with each test number, you have to plug that test number into the autonomous equation and then see whether or not you end up with a positive number or a negative number. Because recall that we're dealing with a derivative here, that being dx dt. And so that means that if we go back to what it means, what a derivative tells us conceptually, that's just the rate of change at any given time, right? So if the derivative is negative, then that tells us that the function is decreasing, and if the derivative is positive, then it's telling us that it's increasing. So plugging the numbers back in, we end up with a negative, and I'm rather than evaluating what the number actually is going to be equal to, I'm going to be focusing more on whether or not we end up with a negative number. So in the case of x is equal to -3, plugging that back into the original equation, we end up with a negative times a negative times a negative times another negative times another negative times another negative, which is ultimately going to give us a positive. And so because we have an even number of negatives, and so since we know that we know that below -2 the function is going to be increasing. So in our number line, I'm going to put an arrow that goes towards, I'll use a different color for that. I'm going to put an arrow that goes towards -2. And then now we have to pick another number that is between -2 and -1, so we can analyze the behavior going on between -2 and -1. So let's just say -1.5. So when x is equal to -1.5, we end up with a negative times a negative times another negative times another negative times a positive times a negative, which is ultimately going to give us a negative because we have an odd number of negatives. And so as a result, we end up with an arrow that goes towards 2 again, between -2 and -1. So now let's test another number. Let's just say x is equal to -0.5. So in that case, we end up with a negative times a positive times a positive times a negative times a positive times a negative. And we have an odd number of negatives, so that's ultimately going to give us a negative. And so that means that we have an arrow that goes towards the -1 away from 0, between -1 and 0. So for the next number, we'd have to do something between 0 and 2, so let's just say 1. When x is equal to 1, we end up with a positive times a positive times another positive times a negative times a positive times a negative, which is ultimately going to give us a positive. So between 0 and 2, the equation is going to be increasing. Now for finally, or no, we have 2 more numbers we have to pick. We have to pick something between 2 and 3, and then something above 3. So let's just say x is equal to 2.5, I guess. Yeah, let's just go with 2.5. So with 2.5, we end up going back, plugging that back into the original equation, we end up with a positive times a positive times a positive times a negative times a positive times a positive. Yeah, and that's ultimately going to give us a negative. And so that results in an arrow that goes away from 3 towards 2. And finally, we can pick one more number, so let's just say x is equal to 4. When x is equal to 4, then we end up with a positive times 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 a positive. Yeah, so all around positive, which ends up being another positive. So that means that we end up with an arrow that goes away from 3 when we're dealing with something above the number 3. So now the next thing we have to do is we need to analyze the way these blue arrows are pointing. So with a stable critical point, so let's just, I'm gonna put a hypothetical graph here. Recall that with stable critical points, let's graph them so we know that x is equal to, let's just say, and I'm gonna put the x values on this axis. And so we know that with a stable critical point, or no, actually no, there's an easier way to explain this. I'll just use the number line. That'll be easier. With stable critical points, we know that with a stable critical point, that means that the function is going to be converging into that critical point. So that means, like, for example, like here at -2, we can see that the arrows are going towards they're both closing in onto -2. A semi-stable critical point is something like what's going on at -1, where you can see that the arrows are both going in one direction, where one arrow is getting closer to -1, while the other one is pointing away. That's the case of a semi-stable critical point. And then an unstable critical point is when both of the arrows are pointing away from the critical point. So it's like a repelling effect. And so looking at this, we have two cases of where the arrows are closing in onto each other, that being at -2 and at, no, wait, +2 and at -2. So from this, we can deduce that there are two stable critical points, which means that the answer to this question is going to be, oh yeah, and then those would just be -2 and 2. So we can deduce that the answer to this question is going to be A. Yeah, because there's two stable critical points. So yeah, so the answer to this question is A. All right, so in this question, we're dealing with our first case of an initial value problem of a homogeneous linear differential equation. And the reason I know that it's homogeneous is because each term has either the function, like the function that we're dealing with, or the derivative of that function. In this case, the function would be y, so this y over here. And so as a result, from here, we'd have to find a general solution and then use that to solve the initial value problem. So we know that when it comes to linear homogeneous differential equations like this, in order to find a general solution, what you're going to want to do is set up a characteristic equation that is, what that is a purely algebraic equation that gets rid of all of the derivatives in the original differential equation, and that'll get you closer to being able to come up with a general solution. So in this case, we can say that the characteristic equation x of r is going to be equal to r squared minus 10r plus 26, where each of these exponents, that represents a derivative. So in this case, we have a y double prime here, so that becomes a second power, and then we have a y prime there, that just becomes a first power, so it's just r. And then you just replace y with r, and then this is just a y, that's not a derivative, so that's like treating it as a constant. And so this is going to end up being our characteristic equation. And we're going to set this equal to 0, because what we need to do from here is solve for r. And that'll allow us to come up with our terms for our general solution. So for this question, well, also, if you look at the answer choices, you can see that each of the answer choices have trigonometric functions in them. So I know that we're going to end up with a case of complex r values. So now it's just a matter of finding out what those r values are. And so to do that, you can we're dealing with a quadratic equation here, so you can either use the quadratic formula or a factor or complete the square. I'm just going to complete the square for this case because that's what I feel like that makes the most sense to me. So when you do that, you end up with r squared minus 10r plus 25. Yeah. Plus 1 is equal to 0, and then this reduces to r minus 5 squared is equal to -1. And so yeah, we're dealing with a complex case here. So taking a square root, we end up with -5 is equal to plus or minus I, which ultimately gives us an r value of r is equal to 5 plus or minus I. And that's a 5, not a b. Okay, and so yeah, so since we're dealing with a case of complex r values, usually when you're coming up with a general solution for a question like this, you maybe come up with an equation that takes the form of like y of t is equal to e to the r value t times some constant. And so if you were to do that with this case, you'd end up with a general solution that looks like y of t is equal to some constant times e to the 5 plus or minus I t, or something like that, right? But we can't really do anything with this because we have an imaginary number here, so we have to take care of that. So we need to rewrite this equation in terms of involving some trigonometric functions. So recall that when you have the case of, we can use an identity. We know that e to the a plus bi t, that's going to be equal to a times e to the at times some constant c sub 1 times cosine of bt plus another constant times sine of bt, where b is the imaginary number and a is the real number of the original r value. So plugging things into this identity, we end up with a general solution that looks like the form of y of t is going to be equal to e to the 5t times some constant c sub 1 cosine of t plus c sub 2 times sine of t. So now that we have our general solution, we can start tackling the initial value problem. And the initial value problem gives us an initial condition in terms of the general solution and an initial condition in terms of the derivative of the general solution. So we're also going to have to differentiate our general solution. So that gives us a derivative of y prime of t is equal to 5 e5t times c sub 1 cosine of t plus c sub 2 sine of t, which is going plus e to the 5t times negative c sub 1 sine of t plus c sub 2 cosine of t. So yeah, so now that we have the general solution and the derivative of the general solution, we can start to plug and chug values and solve the initial value problem. So we know that y of 0 is equal to 1, so plugging those numbers into the original general solution, we end up with 1. 1 is going to be equal to 1 times c sub 1 times cosine of 0 is 1, so c sub 1, and then sine of 0 is 0, so we just end up with 1 equals 1 times c sub 1, so c sub 1 equals 1. We've already taken care of one of the constants from there. Now we can focus on the derivative case. So we know that in the derivative case, we know that 4 is going to be equal to 1 times cosine of 0 is 1 and sine of 0 is 0. So we can get rid of all the sine terms. So we end up with 1 times c sub, or no, 5 times c sub 1 plus 1 times c sub 2. Yeah, 1 times c sub 2. And all we have to do from here, since we already know what c sub 1 is, we just have to solve for c sub 2. And so we know that, so simplifying this down a little bit, we end up with c sub 2 is equal to 4 minus 5 c sub 1. And we know that c sub 1 is equal to 1, so c sub 2 is just going to be equal to negative 1. So now that we've solved both cases, we know what both of the constants are. We know that the particular solution to this initial value problem is going to be equal to y of t is equal to e to the 5t times cosine of t. Oh, my computer is bugging out again. Cosine of, there we go. Okay, I think I fixed it. Cool. Cosine of t minus sine of t after plugging in the constants that we found. So this should be our final answer to this question. So yeah, so the answer to this question is going to be E, I believe. Okay. Let's, all right, yeah. Okay, there we go. Yeah, the answer to this question is going to be E. Okay, nice. All right, given that y sub 1 is equal to x and y sub 2 is equal to 1 over x are two solutions of a second-order linear differential equation, which one of the following functions is the solution to the other differential equation written down here below? So in this question, we have two equations that are very similar to each other, but they're slightly different. So this top equation over here, if my computer, oh, there we go. Okay, yeah, so this equation over here, that equation that takes the form of a homogeneous linear differential equation, whereas this equation takes up the same form, where it's the same equation except it's inhomogeneous. And I know it's inhomogeneous because of this term over here. That term is what makes it inhomogeneous, because in a homogeneous linear differential equation, the right side is always going to be equal to 0, not something else like this. And so we know that for a general solution of a homogeneous differential equation, that usually just takes the form of y of t is equal to y sub c of t, where y sub c, that's the complementary solution of a linear differential equation. And then whereas with the solution for an inhomogeneous differential equation, that takes the form of y of t is equal to y sub c of t plus y sub p of t, where y sub p of t, that's going to be, that part of the solution takes into account having to deal with this inhomogeneous part. And so whereas y sub c of t, the complementary solution is going to end up being the same as this differential equation. And generally speaking, for equations, finding a general solution for a differential equation like this, there's two main ways you can do that. You can approach that. You can either use the method of variation of parameters, or you can use the method of undetermined coefficients. The thing with this question, though, is the fact that it gives us a y sub 1 and a y sub 2 here that are functions rather than constants, as well as the fact that the equations given to us has a p of x and a q of x. We don't know what those are. And so in order to find a solution to this question, the only way we'd be able to do that is by using variation of parameters. And so and we know that with a particular solution usually takes the form of u sub 1 times y sub 1 plus u sub 2 times y sub 2. And in this case, where we just have to come up with a function that represents u sub 1 and u sub 2. And we can do that by using the method of variation of parameters. And to use the method of variation of parameters to find those functions, that's just as, actually, you know what, I'll just keep that here. I'll just put that over here instead. So y sub p of t, or wait, I don't know why I'm writing all of these things in terms of t. I just realized this question is in terms of x. So pretend all of these t's are actually x's. I'll fix that in a second, my bad. So y sub p of t, that's going to be equal to u sub 1 times y sub 1 plus u sub 2 times y sub 2. Okay, yeah, let me get rid of these t's real quick and replace these with x's. So we have an x here, we have an x here, another x here, and another x here. Okay, there we go. All right, now we're good. Now we can proceed. So the next thing we have to do is recall that the formula for the method of variation of parameters takes the form of, where y sub p of t is going to be equal to negative y sub 1 of t. I keep writing t. I'm sorry. That's just a force of habit. Y sub p of x is equal to negative y sub 1 of x times the integral of y sub 2 of x times f of x over the Wronskian of y sub 1 of x and y sub 2 of x plus y sub 2 of x times the integral of y sub 1 of x times f of x over the Wronskian of y sub 1 of x and y sub 2 of x. And once we have all the information that we need for this formula, just evaluating this formula will give us a solution to this question. So the first thing is we know what y sub 1 and y sub 2 are. That's given to us in the question, so I'm going to write those down here. We know that y sub 1 of x is equal to x, and y sub 2 of x is equal to 1 over x. The next thing we have to do is we need to make sure that the equation that we're working with, we need to make sure that the coefficient of the highest derivative is 1. Because if it's not, then you'd have to divide the entire equation by that coefficient to make the highest derivative 1. So in this case, we can see that the highest derivative y double prime, the coefficient is 1. So we don't have to do any of that, so we're good. Because if it was the case where it wasn't 1, you'd have to do a couple of additional steps, and if you miss that, then you'd end up with the wrong answer, and we don't want that. So yeah, and then the next thing we have to do is we need to figure out what the Wronskian is. So recall that the Wronskian, that's going to be the determinant of a square matrix involving the functions that were given to us. So let's say in this case w would be equal to the determinant of y sub 1 of x and y sub 2 of x, and then y sub 1 prime of x and y sub 2 prime of x. And so plugging those values in, this would be equal to the determinant of x and then 1 over x and then negative 1 over x squared. Evaluating this determinant, since we're dealing with a 2x2 matrix here, that's going to be the top left times the bottom right subtracted from the bottom left times the top right. So when we do that, we end up with a Wronskian that's equal to w is equal to, or no, we don't need a determinant there. There we go. That's going to be equal to x times negative 1 over x squared minus 1 times 1 over x. And then that's going to simplify to negative 2 over x. And then the last thing we need to take care of is we need to figure out what f of x is in the formula that we have over here. All f of x is, I'm just using that to denote the inhomogeneous part of the differential equation given to us. Conventionally speaking, usually this 2 over x squared, that's denoted as f of x. So I'll just label that real quick. So that's going to be f of x. So now that we have everything we need, we can plug everything into the formula and evaluate it, and we'll end up with an answer. So we can say that y sub p of x is going to be equal to negative x times the integral of 1 over x squared, or no, 1 over x. So 1 over, that's not what I want, 1 over x times f of x, which is 2 over x squared, over negative 2 over x. And then we have to tack on the second integral, so that's going to be 1 over x times the integral of x times 2 over x squared times negative 2 over x. If I'm not mistaken, and I didn't make any setup errors here, I think that is correct. Yeah, okay, yeah, that's correct. So now we can simplify things a little bit, and so this is going to, this integral is, this can be reduced to negative x times 2 over x squared, no, x cubed times negative x over 2. And I'll put that in parentheses so to avoid confusion, plus 1 over x times the integral of 2 over x, 2 over x times negative x over 2 again. And then you can see from here, a lot of the terms in these integrands are going to cancel, and so these integrals are also really simple to evaluate. So this can also be reduced to the negative x times the integral of these twos cancel as well as these x's, so we end up with just negative 1 over x squared dx plus 1 over x times the integral of just negative 1, because everything here is going to cancel. So yeah, these are really simple integrals, and so this is ultimately going to evaluate to negative x times 1 over x plus 1 over x times negative x. And then when this simplifies, this is going to simplify to negative 1 minus 1, which just equals negative 2. So this is going to be our particular solution to the inhomogeneous part, or yeah, to the differential equation given to us here. And so as a result, we can pick an answer. And so since we know that the particular solution is equal to negative 2, the answer to this question is going to be B. Find the general solution of the given homogeneous differential equation. So in this case, like I said, we're dealing with a higher order homogeneous differential equation. I know it's homogeneous because each term either has a y or a derivative of y, where y is going to be our function, and then also the right side of the equation is just equal to 0. And so as a result, that makes it a homogeneous differential equation. So as a result, we can find our general solution by setting up a characteristic polynomial and then using that characteristic polynomial to come up with a set of linearly independent terms for our general solution. And recall what that is we're just going to be setting up a purely algebraic polynomial where that doesn't have any derivatives in it. So let's just say x of r. And I'm going to set that equal to r cubed plus 6r squared plus 9r and set that equal to 0. And what I basically did here is I translated each derivative into an exponent instead. So this third derivative just became a third power, the second derivative became a second power, so on and so forth. And then from here, we set this equal to 0, and then we have to solve for r. And so when you do that, you should end up with an equation that takes the form of r times, or however you're comfortable with. I'll just split this up and solve for r. So r times r squared plus 6r plus 9 is equal to 0, which is going to split up into r times r plus 3 times r plus 3, which is equal to 0. And that's going to give us r values of r is going to be equal to 0, negative 3, and negative 3. So negative 3 with a multiplicity of 2. Emphasis on multiplicity of 2 because that's going to affect our general solution. So from here we can just we can come up with our terms for our general solution. So we can say that y of t is going to be equal to some constant times e to the rt, and the amount of terms you have is dependent on how many r values we have. So we have 3 r values, so we'll have 3 terms. So we'll end up with something that looks like c sub 1 times e to the 0t plus c sub 2 times e to the negative 3t plus c sub 3 times e to the negative 3t. The problem is this solution is not actually going to be valid because not all of the terms are linearly independent. I mentioned how we have I mentioned here how we have an r value of -3 with the multiplicity of 2. And so as a result, that means that we have duplicate terms here, and these terms are not going to be linearly independent. We need to change up one of the terms to make it linearly independent. And so what that entails is just attaching a t to one of these terms, and that will make it linearly independent. And so now that we've done that, yeah, similarly, and you have to do that process for no matter how many repeated r terms you had. So like let's say we had 3 or -3 with a multiplicity of 3. Then we'd have a fourth term of c sub 4 times t squared times e to the -3t. And then you'd keep increasing the power of t the more repeated terms you have. And so yeah, so now this is a valid general solution. So we can simplify this a little bit. Since we have an e to the 0t, that can just simplify to y of t is equal to c sub 1 plus c sub 2 e to the -3t plus c sub 3t times e to the -3t. And so now this is going to be our final general solution for this differential equation. Another thing that I'm going to mention is you can also automatically eliminate answer choices C and E in your computational process because those answer choices have a sine and cosine term in there. And the only way to end up with a sine and cosine term is if you end up with a complex r value, but we didn't have that. All of our r values were real. And so as a result, there's not a case where we'd end up with sine and cosine terms in our general solution. So now we can compare this with our answer choices, and that matches up with answer choice A, I believe. Yeah, so the answer to this question is going to be A. Okay, so in this question, we're dealing with a inhomogeneous higher order differential equation, and it's asking us to find a particular solution for that inhomogeneous differential equation using the method of undetermined coefficients. So recall that in the case of an inhomogeneous differential equation, we know that this differential equation down here, that's inhomogeneous because the right side of the equation is not equal to 0. And so as a result, our general solution is going to be the process of setting up the general solution is going to be a little bit different than in the case of a homogeneous differential equation like we have up here, where we know it's homogeneous because, well, the question says it is, but also the right side of the equation is equal to 0. So recall that to find the general solution of a homogeneous differential equation, that would take the form of, in this case, y of t would be equal to just y sub c of t or something. Or no, y sub c of x. Sorry, but if I say c around this explanation here and there, I mean x. That's just a force of habit. So yeah, let me rephrase. Y of x would be equal to y sub c of x. And then in the case of an inhomogeneous differential equation, the general solution would take the form of y of x is equal to y sub c of x plus y sub p of x. And y sub c of x here, that's going to be the same y sub c here, because we can see that this side of the equation is equal to this side of the equation, so the homogeneous part. And then the particular solution, the y sub p term, that's going to take care of this side of the equation. So now we can proceed with finding the particular solution. But since we're using the method of undetermined coefficients to do that, we still need to find our complementary solution. We can't just jump straight into setting up our particular solution because the way our particular solution is going to be set up is dependent on information in the complementary solution. Because with the method of undetermined coefficients, we're coming up with like an educated guess that is based on the right side of this equation and comparing it against our complementary solution and making sure that we don't have any conflicting terms. Because if you have conflicting terms, then it's not going to be a valid general solution. Where basically, and the reason why is basically if you have an invalid guess, recall that let's say like we know that when you're finding a particular solution using the method of undetermined coefficients, they take up the form, your solution is going to take up the form of the stuff we see here, where you can see like a, b, c, d, e. And in order to solve for those a, b, c, d, e terms, you'd have to plug it back into this differential equation and solve for it. And if you have an invalid particular solution guess, then when you plug it back into the equation, you're going to end up with some wonky equation that's not going to give you the right numbers. And so that's why you need to compare it with your complementary solution to make sure that you don't have any conflicting terms. So now I'll start with that. And then also, I'm going to just rush through the complementary solution computation because I want to mostly focus on the particular solution for this question. So if you're not comfortable with finding complementary solutions, I would suggest just practicing some more questions that deal with purely homogeneous differential equations so you can get more comfortable with that. So rewriting our characteristic polynomial down here, we can split that up into r squared times r squared, or no, r squared minus 9 times r squared minus 9r plus 10. Splitting that up again, we end up with r times r plus 3 times r minus 3. And then I'm going to evaluate this polynomial separately because that's going to give us a complex r value. So completing the square for this one, we can say that r squared minus 9r, or oh no, my bad, this is supposed to be a 6, my bad. Okay, so cleaning that up real quick, we end up with 6, 6, 6, and 6. So r squared minus 6r plus 9 is going to be equal to, oops, get rid of that, there we go, is going to be plus 1 is equal to 0, and then r minus 3 squared is going to be equal to -1, so r is ultimately going to be equal to 3 plus or minus I. And so from here, then the remaining r values, those are going to be equal to 0, 0, 3, and -3. And so now we can come up with our complementary solution, which is going to be equal to y sub c of x is equal to c sub 1 plus c sub 2x plus c sub 3 times e to the 3x plus c sub 4, c sub 4 times e to the -3x plus e to the 3x times c sub 5 cosine of x plus c sub 6 sine of x. So now that we have our complementary solution, now we can start focusing on our particular solution. And recall that now I'm going to just be focusing on this side of the equation. So when you see there's a general set of rules to follow when you're using the method of undetermined coefficients to come up with an educated guess. And what that entails, I'll write those rules over here. So we know in the case of, like, if you see a constant term, so if you see just a c term, then your guess is just going to be a letter, so just a or something, a, b, whatever. And then if you see get rid of that again, if you see like an e to the something, let's just say rx, then that's going to turn into a b times e to the rx. And then if you see an x attached to that, then it's going to turn into b to the rx times x plus c to the e rx. And then if you see like a sine of rx term, or a sine or cosine of rx term, then your guess is going to consist of an e times the sine rx plus f times cosine of rx or something. And then similarly, if you see an e term attached to that, to those sine or cosine terms, then you'd also attach an e to your guess. And so comparing those rules to our answer choices here, we can come up with an initial guess that is going to be equal to y sub p of x is going to be equal to a plus bx times e to the 3x plus c times e to the 3x plus d times sine of 3x plus e times cosine of 3x. Another way you can look at it, if those rules that I mentioned don't make sense to you, another way you can look at it is basically a method of undetermined coefficients for a question like this. You can treat it as like you're solving an initial value problem backwards, because these rules that we follow for an educated guess, they're basically, our guess is following the general form of what this would be equal to, say, if it was like a complementary solution that came from another differential equation. So what I mean by that is, like, let's say that this was a general solution to another differential equation, and we had to solve an initial value problem to end up with this term. When you solve that initial value problem, you can solve for this a, b, c, d, and e term, and you'll find that a is going to be equal to 1, b is going to be equal to 4, c is going to be equal to 0, d is going to be equal to -1, and e would be equal to 0. And when you plug in these numbers that I came up with, you'd end up with this term over here. So that's what I mean by it's like solving an initial value problem backwards. You're basically trying to decipher this and turn it back into its general form where you didn't know what the constants for your solution was equal to, if that makes sense. Hopefully it does. That's just the way I like to look at method of undetermined coefficients. So now that we have our initial guess, the next thing we have to do is we need to compare that with our complementary solution and make sure that we don't have any conflicting terms. And I can see right away that we do have some conflicting terms. So you can see here, this c e to the 3x conflicts with this c sub 3 e to the 3x. You can see that they take up the same form because we have a constant here and a constant here, and then we have an e to the 3x term and an e to the 3x term there. So for all intents and purposes, for this question, those terms are going to be identical, which would mean that they're not going to be linearly independent. So we're going to have to change up our particular solution guess a little bit. And the first thing that would entail is I'm going to attach a t to this term. It's similar to when you're dealing with the case of repeated r values for a complementary solution, where you attach a t to each repeated term to make each of them linearly independent. And so doing that, I'll turn this into c times x to the e 3x. And now checking for conflicts again, we can see that this ends up conflicting with this term now, because now these two terms take up identical forms. So we're also going to have to change this term. And I'm going to add an x to this one as well, so that becomes bx squared times e to the 3x plus cx e to the 3x. And that will ultimately get rid of all of the conflicting terms with our complementary solution. Now the next term that we have that's conflicting is this c sub 1 and this a. We can see that they're both constants, so for the sake of this question, they're going to be identical. And so I'm going to have to attach an x to a as well, making it ax plus this thing. But we still have a conflict because even after I added this x, you can see that now it's conflicting with this c sub 2x. And so I'm going to have to turn this into an x squared as well to get rid of the conflicts with this term as well as this term. Now that we've done that, now I think we've pretty much sorted out everything that we need to do. And so as a result, now we can finish up our final particular solution, and we can say that y sub p of x is going to be equal to ax squared plus bx squared e to the 3x plus cx e to the 3x plus d sine of 3x plus e cosine of 3x. And so now that we have this, now we can compare this with our answer choices. And that matches up the closest with answer choice D, with the only difference being that they set their cosine term, they put the cosine term before the sine term, whereas I put the sine term before the cosine term. But you can probably see how they take up the same form. So the order there doesn't really matter. They'll be the same. And so yeah, so as a result, the answer to this question is going to be D. Yeah. Okay, so in this question, we're given an initial value problem, except it's asking us to approximate that initial value problem using Euler's method. So recall that Euler's method, that is an approximation method like the question is saying. So for this initial value problem, we're not going to get an exact answer, rather we're going to get an approximate answer. And so to do that, we're going to have to use the formula for Euler's method and keep running through that formula until we reach our target approximation. And so we know that our target approximation is y of 2 as written here. And so to start, let me write out the formula for what Euler's method is. So recall that that's going to be y sub n plus 1 is equal to y sub n plus h times f prime of x sub n and y sub n. And so what each of these terms means, so I'll start with h. So h, that's going to be our step size like written here. And then the f prime of x sub n and y sub n that's written here, that's just going to be the differential equation that was given to us, so this. And x sub n and y sub n, those are going to be, I guess I'm going to call them our control variables, because those things are going to change with each pass of Euler's method that we run through. And they start off and basically we use the initial condition given to us as a starting point. So let's just say when n is equal to 0, since I'm going to treat n equals 0 as our initial condition case. Our initial condition tells us that y of 0 is equal to 3. So x of 0 is going to start off being equal to 0, and y sub 0 is going to start off being equal to 3. And then what we do is, now what we want to do is we want to find the next term, so the case of when n is equal to 1. And so in that case, the way we find that is by using the x how should I put it? Yeah, the x sub n values and y sub n values from like our first pass. We use that to find the next value, if that makes sense. So in the case of x sub 0 and y sub 0, we have those values, and so now we want to find y sub 1. So in the case of y sub 1, or actually, and then another thing I'm going to do is I'm also going to write a table to keep track of everything to make it a little more clear. So I'll have 3 columns, so n, x sub n, and y sub n. And we're going to start with our initial conditions and then n equals 0. So 0, 0, and 3. And before I do anything further, let me also focus on how the step size works, so that being h. That step size is going to change what? That's going to change what x sub n is. Because what you'll see is that the formula for Euler's method, that gives us the following y sub n term, but we still need to figure out how to change x sub n. That's what the step size is going to do for us. The step size is going to change x sub n for us, if that makes sense. And so and then the way we know when to stop in terms of passes, like how many passes of Euler's method we want to use, we want to keep running through the formula and coming up with new terms until you reach our target of y of 2. And since we're starting at y of 0 and we have a step size of 1, we're going to go up by increments of 1. So 0, 1, and then 2. So we're only going to have to do 2 passes of Euler's method to find an answer to this question. So let me put in the next value. So the case of when n is equal to 1, to find y sub 1, we're going to use y sub 0, our previous value of 3, plus our step size h, which is 1, times the differential equation where we're plugging in our x sub n and y sub n values. And so when we do that, we end up with an equation that takes the form of 0 plus 2 times 3. And then that's going to simplify to 3 plus 6, which is equal to 9. And so now we have y sub 1. So I'm going to put that here. And we know that x sub n is now going to be equal to 1 because the step size incremented it up by 1. So in the case of, like, for example, in the case of if the step size is 0.5, then the following x sub n term would have been 0.5 rather than 1, if that makes sense. And so now to find the second term, y sub 2, now that's going to be equal to the previous numbers that we had here. So last time we used 0 and 3 as our control variables. Now we're going to use 1 and 9. So now instead the formula is going to take the form of 9 plus our step size times plugging in our new values. It's going to be 1 plus 2 times 9. And then when you simplify that, that's going to equal 9 plus 1 plus 18, which equals 28. And that's going to give us y sub 2. And so now we have completed what we have to do. We've reached y of 2 here. And so now that's how we know that we can stop. And so now we can pick an answer. So we know that at y sub 2, we know that's going to be equal to 28. So the answer to this question is going to end up being E. Alright, so given the phase portrait of the system x prime is equal to ax, what are the possible eigenvalues of the matrix A? So we're dealing with the case of basically the phasing behavior of a system of differential equations and the general solution for that system. And usually recall that in the case here, we have a spiral. And the only way to end up with a spiral is if you have complex eigenvalues. You can't get a spiral when you have real eigenvalues. And so as a result, we can automatically rule out 3 answers right away. We can get rid of B. Yeah, we can get rid of B, we can get rid of D, and we can get rid of E, because those are all real eigenvalue cases. So now the next thing I'm going to do is I'm going to put some graphs here. So I'm going to put a graph here, and I'm going to put a graph here. In the case of now I'm only going to focus on complex eigenvalues. So let's just say A plus or minus BI. In the case of in order to end up with a spiral, you need to have either a positive A or a negative A, but not 0. So that would mean that your complex number, you have a real part and an imaginary part. So we'd say that A has to either be less than 0 or no, greater than 0 or less than 0, but not equal to 0. And then in that case, when you have that case, then you'll end up with a spiral. And depending on whether A is positive or negative, you'll end up with a spiral source or a sink. But the difference between a source and a sink is not relevant to this question, so I won't go too in depth with it. What I will focus on is the difference between whether or not A is equal to 0. In the case when A is equal to 0, where your eigenvalue is purely imaginary, so you only have a BI, then you're going to end up with a center. So you'll notice that, you're going to end up with a center, so it's going to look like this, where you just have circles or ovals, but they're not spiraling. Like, they stay in place, if that makes sense. Like, you'll see here in this case, like it's getting bigger and bigger and bigger, whereas in this case, these circles, they stay together and they don't change. So this graph would be the case where you have A is not equal to 0, and then this is the case where A is equal to 0, just to simplify things. And so that also gets rid of the answer choice A, because in the answer choice A, you can see here that A is equal to 0 because that's equal to 0 plus or minus 5i. And then in C, we can see that A is equal to -1. So this would be, And so as a result, since we're dealing with a spiral here, we'd end up with C. And then because if we were dealing with the case where if this graph looked like this graph, then it would be A. But since it looks like this and not this, or no, since this graph looks like this graph, it's going to be C, because A isn't equal to 0, if that makes sense. So the answer to this question is going to be C. Okay, so in this question, it's asking us to find the matrix exponential e to the at for the matrix A given to us. So what that entails is, the first thing we have to do is we're going to have to treat this matrix as if it's coming from a system of differential equations where we're effectively trying to find the linearly independent the linearly independent solutions to come up with a general solution for the system. And what that entails is we'd have to find the eigenvalues and corresponding eigenvectors of the matrix given to us, and then we can use that information to then calculate the matrix exponential. So to start, I'll go through finding the eigenvalues and eigenvectors of the matrix. So recall that in order to do that, you'd have to set the determinant of A minus lambda I equal to 0. So what that's going to look like is the determinant of A minus lambda I is equal to 0, where A is the matrix given to us here, and then minus lambda I, that's going to be the identity matrix with negative lambda, so that's going to look like minus lambda, like this. And so what that looks like once we plug everything in, we should end up with a determinant that looks like 1 minus lambda, 2, 2, and 1 minus lambda, and set that equal to 0 and find that determinant. And recall that in order to find the determinant of a 2 by 2 matrix, that's multiplying the top left by the bottom right and the bottom left, and then subtracting the bottom left by the top right. And so that's going to look like 1 minus lambda times 1 minus lambda minus 4 is equal to 0. And when you simplify this down, you'll end up with a term that looks like lambda squared minus 2 lambda minus 3. I think and so you should end up with a term that looks like that, setting that equal to 0. And this quadratic expression is pretty easily factorable, so when you do that, you end up with a factored form of lambda plus 1 times lambda minus 3 is equal to 0, giving us lambda values that are equal to -1 and 3. And so these are going to be our eigenvalues for this matrix. And now we can use that information to find the corresponding eigenvector. And that involves plugging in your eigenvalues back into this matrix to come up with the eigenvectors. So that's going to look like you'd have an expression that looks like this. So starting with the first eigenvalue of lambda, let's use 3 first. Starting with lambda is equal to 3, when you plug that back into this matrix, you should end up with a matrix that looks like -2, 2, 2, and -2. And I'm going to multiply that by a vector that includes x sub 1 and x sub 2, and we're going to set that equal to the 0 vector, and then solve this, right? And then from here we have to pick two numbers for x sub 1 and x sub 2 that aren't 0 and 0 that satisfy this expression. And so from here, I'm going to do a little bit of matrix multiplication, and that'll give us an expression. I'll use the top row, so I'll use this row for that, and we end up with negative 2 times x sub 1 plus 2x sub 2 is equal to 0. Simplifying this expression a little bit, we end up with x sub 1 is equal to x sub 2. And so when you're setting up your eigenvectors, you want to pick the simplest numbers you can think of. So I'll just use 1 and 1. So v sub 1 is going to be equal to, that's just going to be equal to 1 and 1. And then for the second case, so lambda is equal to negative 1, we rinse and repeat the same process of plugging in the values into this matrix and running through this process again. And we end up with a matrix of 2, 2, 2, and 2, multiplied by x sub 1 and x sub 2 equal to 0 and 0. Setting up an equation, we end up with x sub 1 plus 2, no, 2x sub 1 plus 2x sub 2 equal to 0. Simplifying this down, we end up with x sub 1 is equal to negative x sub 2, and we can come up with a corresponding eigenvector. I'll just use 1 and negative 1. And so now that we have our eigenvalues and our corresponding eigenvectors, we can come up with our linearly independent solutions. So let's just say that x sub 1 of t, that's going to be equal to e to the 3t times its corresponding eigenvector of 1 and 1, and then x sub 2t, that's going to be equal to e to the negative t times e to the negative t and negative e to the negative t on the bottom, like this. Or wait, yeah. Or let me split it up to make it more obvious. So e to the negative t times its corresponding eigenvector of negative 1 and 1. And so now that we have our two linearly independent solutions, now we can start to focus on computing the matrix exponential. So moving up over here, recall that in order to do that, there's a formula for that. So we can say that e to the at, that's going to be equal to the fundamental matrix, which I'm going to denote as phi, times the inverse of our fundamental matrix evaluated at 0. And once we compute these things, that's going to give us our matrix exponential. And recall that the fundamental matrix, all that is that's just combining our solutions and mashing it into a single matrix. So what that entails in our case is, for here we distribute this e term with its corresponding eigenvector, and then this e term with this corresponding eigenvector, and to simplify it a little bit, and then mash those two solutions together, and that'll give us a 2x2 matrix. That would give us our fundamental matrix. And then the next thing I'm going to do, now it doesn't matter the order in which you do it in, but for this case, what I'm going to do is I'm going to specifically set up our fundamental matrix to look like this, where phi of t is going to be equal to e to the 3t. So this solution, I'm going to put this solution on the left side of the matrix and this solution on the right side of the matrix. And the reason why I'm doing that is so I can match it up with our answer choices here. You can see how the answer choices do it that way as well. You could do it the other way around as well and still come up with the correct answer, but it wouldn't match up with the answer choices, and so you'd be giving yourself extra work of doing like the conversion. So I don't want to deal with that, so I'm going to set it up this way. And so we end up with a fundamental matrix that looks like this, where we have e to the 3t, e to the 3t, e to the negative t, and negative e to the negative t, like this. And now we can start focusing on finding the inverse of our fundamental matrix. And recall that in the case of 2x2 matrices, there are two ways that you can find the inverse of a matrix. So you can either do the normal way, which is where you set up an augmented matrix that looks like this, where you have the original matrix on this side. So you have the original matrix here, and then you have pivot columns on this side, so 1 and 1 like this. And then you can row reduce this augmented matrix, and then that'll give you a new form where after you row reduce it, you have your pivot columns on this side, and then you have a new matrix on this side, and this is going to become your matrix inverse. And now, that's the more generalized approach of finding the inverse of a matrix. And also you'd have to be pretty comfortable with linear algebra to do that, which I know not everyone is. So if you don't want to do that, there is a formula for finding the inverse of a 2x2 matrix as well. And what that formula is where let me use a different matrix. Let's just say g of t, and let's set that equal to a, b, c, and d. What the inverse of g of t is going to be, that's going to be equal to 1 over the determinant of g of t, so that's going to be ad minus cb times its adjugate matrix. And in the case of a 2 by 2 matrix, an adjugate matrix, that's going to be where we flip the positions of a and d and then flip the signs of c and b. So you're going to end up with a matrix that looks like d, a, negative c, and negative b, like this. And then from there, it's just plugging in and computing and distributing the fraction that we have over here into the matrix, and you'll have your matrix inverse. And then let me also get rid of this. I'll come back to this later, because I do want to show both approaches so you can be familiar with both approaches and just pick which one you're more comfortable with. Personally, for questions like this, I think it's easier to use the formula, but if you don't want to do that, you can still do it the old-fashioned way. And then also another thing that I'd suggest to make things easier, in this case specifically, since we're finding the inverse at 0, it would be easier to plug in 0 beforehand into these e terms. It'll be easier to plug in 0 beforehand and then do the inverse computation, because you won't have to be dealing with a bunch of e terms, if that makes sense, and computing that determinant is going to be a lot more tedious. So I'm going to do just that. So I'm going to say that phi of 0, our fundamentals matrix evaluated at 0, when we plug in 0, we end up with 1, 1, 1, and negative 1. So now we can compute the matrix inverse. So that's going to be equal to phi inverse of 0 is going to be equal to 1 over the determinant of phi of 0. So that's going to be negative 1 minus 1. And then put in the adjugate matrix. So negative 1, 1, negative 1, and 1, like this. And then that's going to simplify to phi inverse of 0 is equal to just 1/2, and then negative 1/2, and then 1/2 again, and then negative 1/2, if I'm not mistaken. If I didn't make any mistakes, this should be our matrix inverse, and we can plug things back into our, we can plug things back into our, oh, I realized I did make a mistake actually, my bad. Yeah, no, I made a mistake in the adjugate matrix. There should be a negative here, my bad. Let me clean this up a little bit. So then we end up with a matrix that looks like this. And then we can simplify. So from here, like this fraction that simplifies to just, I'm going to simplify that down to negative 1/2. And then distribute it. And so we end up with 1/2, 1/2, 1/2, and negative 1/2. So now we have the matrix the inverse of our fundamental matrix evaluated at 0, and we can put that next to our original fundamental matrix as well, and we'll end up with our answer. So we can, moving an arrow down here, we can say that e to the at is ultimately going to be equal to e to the 3t, e to the negative t, e to the 3t, and negative e to the negative t times its inverse at 0, which is 1/2, 1/2, 1/2, and negative 1/2. And the cool thing is, our answer choices have the answer set up like this. We don't have to do the matrix multiplication to simplify this, which would add a whole nother level of tediousness. So that's nice. So matching this up with the answer choices, the answer to this question is going to end up being equal to B. So so the answer to this question is going to be B. Now from here, if that's all the information you want from this question, you can move on. And then now I'll show you how to find the inverse the normal way if you're curious, if you want to do it that way. So what that would entail is so we can say that let's put in our original phi of 0 over here. So we're going to end up with an augmented matrix that looks like 1, 1, 1, and negative 1, and then 1, like this. And then we have to do a bunch of row reductions, and that's going to give us that's going to give us the matrix inverse. So the first thing I'm going to do is I'm going to denote this as R sub 1 and R sub 2. And the first thing I'm going to say is the first pass I'm going to do is I'm going to set r sub 2 equal to r sub 2 minus r sub 1. And so I'm going to multiply the top row by -1 and subtract it from the bottom row, and that's going to turn into 1, 1, 0, and then -2, and then 1, 0, -1, and 1, like this. And then the next thing I'm going to do is I'm going to adjust the bottom row again and say that r sub 2 is equal to just 1/2 r sub 2. And then that's going to turn the bottom row into 1, 1, or no, I'm going to set r sub 2 equal to -1/2 r sub 2 because we want this in row reduced echelon form. So that's going to give us 1 and then 1/2 and then -1/2 here. And we're almost there. We almost have our two pivot columns on the left side here. So all we have to do is get rid of this one. And so in order to do that, we just have to do one more pass of a row reduction and say that r sub 1, that's going to be equal to r sub 1 minus r sub 2. And that's going to give us a final row reduced matrix of 1, 1, 1/2, -1/2, and then 0, 1/2, and 1/2. And so you can see here that now that from here now we have this completed in row reduced echelon form. And so now you can clearly see how the matrix inverse is going to be equal to this. And so yeah, so that's how you would find the inverse of the matrix the normal way. So yeah, and so yeah, that should finish everything for this question. So I'll zoom out so you can see everything. Okay, cool, nice. All right, so this is going to be the first initial value problem of a system of differential equations rather than just a single differential equation. So as a result, since we're dealing with a system, that means that in order to solve this initial value problem, we're going to have to use the eigenvalue method to come up with a general solution and then go from there to solve the initial value problem. So to start, before I do anything, I'm going to call this matrix A, because it'll just to make things a little easier to explain from here. And so recall that when using the eigenvalue method to solve problems like this, you're going to want to find your eigenvalues of your matrix A and the corresponding eigenvectors. So in order to do that, recall that to find an eigenvalue, you have to set the determinant of A minus lambda I equal to 0, where A is the matrix given to us here, and then minus lambda I, that's going to be your identity matrix that looks like this. So plugging in your values, you should end up with a determinant that looks like -1 minus lambda, 1, -3, and -5 minus lambda, and set that equal to 0. And then to find the determinant of a 2 by 2 matrix, recall that that's multiplying the top left by the bottom right, and then subtracting the bottom left times the top right from that. So you should end up with an equation that looks like -1 minus lambda times -5 minus lambda plus 3 is equal to 0. When you simplify this down, you should end up with a quadratic expression that looks like lambda squared plus 6 lambda plus 8 is equal to 0. And then this is pretty easily factorable. When you factor this, you should end up with lambda plus 2 and lambda plus 4 is equal to 0. And solving for lambda, you should end up with eigenvalues that are equal to, let's just say, I'll write that over here. Lambda is going to be equal to -2 and -4. So now that we have our two eigenvalues, we can plug these eigenvalues back into this matrix to find our eigenvectors. So what you're going to want to do is you're going to, let's just start with the first eigenvalue of -2 and plug that back into this matrix. And so you should end up with a matrix that looks like, so in the case of lambda is equal to -2, you should end up with a matrix that looks like, let me get rid of that, oops. By the way, this is a little unrelated. If somebody knows of a good stylus, a stylus that has good palm rejection, please hit me up, because that'll help me with not accidentally writing random crap sometimes. So anyway, plugging in the first eigenvalue of -2, you should end up with, like, this is what I was talking about. Okay, 1, 1, -3, and -3. And then the next thing you're going to do is multiply that by x sub 1 and x sub 2. basically this vector given to us in the original equation, and then set that equal to the 0 vector of 0 and 0. And then from here, you're going to want to pick two numbers for x sub 1 and x sub 2 that satisfy this expression that aren't 0 and 0. And the way you can find those values, you can either do you can do some row reductions, or you can just do some matrix multiplication to come up with an expression to do that. So I'll do the latter because I find that for the case of 2 by 2 matrices, it's easier to just do that. So we can say that using the top row, so this 1, 1, we can say that x sub 1 plus x sub 2 is equal to 0. And then simplifying this, we can end up with x sub 1 is equal to negative x sub 2. And also for your eigenvectors, even though you can pick any two numbers that aren't 0, 0, try to pick the most simple numbers that you can think of, because usually for exams like this with multiple choice questions, they're gonna the exam themselves, they're going to pick the most simple numbers. So for our first eigenvector, we can just use 1 and negative 1, and that'll satisfy this equation. So now, or you can use negative 1 and 1 with the top and bottom flipped. Either one is valid, but I'm just going to use this one. And so the next thing you want to do is rinse and repeat this process for the second eigenvalue. So in the case of lambda is equal to negative 4, you should end up with an expression that looks like 3, 1, negative 3, and negative 1 times x sub 1 and x sub 2 is equal to 0 and 0. And then doing the same process, I'll use the top row again. You should end up with 3x sub 1 plus x sub 2 is equal to 0, which simplify this, we can end up with 3x sub 1 is equal to negative x sub 2, and then come up with a corresponding eigenvector where I'm just going to pick the opposite numbers for x sub 1 and x sub 2. So I'll say negative 1 and 3, like this, because those are the most simple numbers I can think of. And so now from here, we can come up with our general solution. And that's just as simple as attaching an e to the lambda t term to each of our eigenvectors. So you should end up with a general solution that takes the form of, let's just say that x sub 1, x sub 2 is going to be equal to some constant times e to our first eigenvalue of negative 2t times its corresponding eigenvector of 1 and negative 1, plus c sub 2 times e to the negative 4t times its corresponding eigenvector of negative 1 and 3. And so now that we have our general solution, we can start to solve our initial value problem. So I'm going to, so moving over here a little bit, we know that for our initial value problem, we're given this initial condition. And so for that, we can set up an expression saying that the vector, let's just say 1 and negative 5. Let me move an arrow here. So let's just say, so you can see what I'm doing here. We can say that, or yeah, let me move this. Let me clean this up a little bit. This can be neater. Like this. We can say that 1 and negative 5 is going to be equal to c sub 1 times its corresponding eigenvector of 1 and negative 1. I got rid of the e terms because the initial condition tells us what these numbers are when x sub 1 and x sub 2 are equal to 0, as you can see here. So that would get rid of the e term, plus c sub 2 times negative 1 and 3. And so from here, all we have to do is solve for c sub 1 and c sub 2. And there are two ways you can do that. You can either distribute the constants into its vectors and then set up a system of equations and go from there, or you can just plug all these numbers into an augmented matrix and row reduce it. So I'll show both approaches. So I'll start with the system of equations way. So distributing our constants, you should end up with 1 times c sub 1 minus 1 times c sub 2 is equal to 1, and then negative 1 times c sub 1 plus 3 times c sub 2 is equal to negative 5. So the first thing that I'm going to do is I'm going to set up a substitution so we can say from here, well, also let me simplify these expressions as well. These can simplify to c sub 1 minus c sub 2 is equal to 1, and negative c sub 1 plus 3 c sub 2 is equal to negative 5. So the first substitution I'm going to do, I'm going to say that c sub 1 is going to be equal to 1 plus c sub 2, and then, let me put some arrows so you can see the direction I'm going in. So then we can say that, yeah, c sub 1 is equal to 1 plus c sub 2. because I just moved this C sub 2 to the other side. And then plugging that into this expression, we should end up with negative 1 minus C sub 2 plus 3C sub 2 is equal to negative 5. And from here we can solve for C sub 2. Simplifying this, we can end up with 2C sub 2 is equal to negative 4. And so C sub 2 is ultimately going to be equal to negative 2. And then we can plug that back into this expression, this expression, and solve for C sub 1. So when we do that, we can say that C sub 1 plus 2 is equal to 1. So C sub 1 is just going to be equal to 3. And so yeah, now that we have our two constants, we can plug that back into our differential equation. Now, if you were to do this with a row reduction, you'd set up an augmented matrix that looks like this. You'd say that 1, negative 1, negative 1, 3, bar, 1, and negative 5. And then you can do the row reduction. So for this, I guess I'm going to cancel out some stuff in the bottom row, so we can say that r sub 2 is equal to r sub 2 minus r sub 2 plus r sub 1, which is going to give us a new matrix that looks like 1, negative 1, 1, 0, and then 2, and then negative 4. Then we can do another pass to simplify the bottom row again and say that r sub 2 is going to be equal to 1/2 r sub 2, which is going to give us a new matrix that looks like 0, 1, negative 2, negative 1, and 1. And then we can complete this row reduction by saying that r sub 1 is finally going to be equal to r sub 1 plus r sub 2, which is going to give us a term of 1, 1, 1, 0, and negative 1. Did I do something? Oh, I see what I did wrong here. Yeah, so, and then I just realized I made a mistake in our other process. C sub 1 should actually be equal to negative 1, not 3. Okay, now everything is matching up. So you can see in both cases, we end up with a case where so this is going to be equal to C sub 1, and this is going to be equal to C sub 2. So now that we've found those two cases, you can see in both approaches, you can do whichever one you're more comfortable with. Personally, I think for questions like this, I like to do row reductions more, but that's just me. Anyway, let's plug that back into our general solution. So you should end up with a particular solution that's equal to, let me condense things a little bit. Let me move this somewhere else. Let me shrink this and then move that over here, and then shrink it again. Okay. So now, going back to the original problem, we can say that the particular solution to this question is going to be equal to, let's just say, x sub 1, x sub 2 is going to be equal to negative e to the negative 2t times 1 and negative 1 plus, or no, minus 2 times e to the negative 4t times its corresponding eigenvector of negative 1 and 3. And the question is asking us to find x sub 1 of t. So that's just going to be, it's asking us like the top row of our vectors. So all you have to do is just distribute these e terms with the top numbers of our vector. So we can say that x sub 1 is going to ultimately be equal to negative e to the negative 2t plus 2 times e to the negative 4t. So this is going to be our final answer to this question. And matching that up with the answer choices, that matches up closely with answer choice, I believe that matches up with A. Yeah, so I think the answer to this question is A. Yeah, the answer to this question is going to be A. All right, so in this question we're dealing with another linear system, and it's asking us to find the general solution of it. So looking at all of the answer choices, I know right away that we're dealing with the case of defective eigenvalues. You can see this because when you look at the answer choices, you'll notice that each of the e terms have a negative. They each have a negative 4 attached. So that tells us that we're dealing with defective eigenvalues, or more put simply, repeated eigenvalues. Not to mention the fact that the corresponding vector for the solutions, these each have a t somewhere in the vector. that also tells us that we're dealing with a case of defective eigenvalues. And if you're not, and so from here we can deduce that the eigenvalues we're dealing with are going to be lambda is equal to -4 and -4. So -4 with a multiplicity of 2. Now, if you're still not convinced, you can still just do the computation manually. So to do that, you'd set the determinants of a minus lambda I equal to 0, where this is going to be a. That's, yeah, so that we're the given matrix, I'm going to call this a. And so you should end up with a determinant that looks like -6 minus lambda, -1, 4, and -2 minus lambda is equal to 0. And then when you do this computation, solving for lambda, take this determinant, you should end up with -6 minus lambda, -2 minus lambda, plus 4 is equal to 0, which simplifies to 12 minus, 12 plus 8 lambda plus lambda squared plus 4 is equal to 0, which simplifies to lambda squared plus 8 lambda plus 16 is equal to 0. And then factoring this out, you should end up with lambda plus 4 and lambda plus 4. And then that ultimately gives us lambda is equal to -4 with a multiplicity of 2. So yeah, now that that's out of the way, now let's start focusing on the computation for the general solution. So the first step is, what you want to do is you want to find an eigenvector, just one. Since we only have one eigenvalue that is repeated, we're just going to find one eigenvalue, corresponding eigenvector, and then the process from there is going to deviate a little bit. So to do that, what you're going to want to do is plug in your eigenvalue back into this matrix. And so you should end up with a matrix, so in the case of lambda is equal to -4, you should end up with a matrix that's equal to -2, -1, 4, and 2. Yeah. And then you're going to want to multiply this by, let's just say, x sub 1 and x sub 2. So a vector of the system, and set that equal to the 0 vector. And then pick two numbers for x sub 1 and x sub 2 that satisfy this equation that aren't equal to 0 and 0. And so doing that, I'll just use the bottom row this time, because I just like that there's only positive numbers in that case. So we can say that 4 times x sub 1 plus 2 times x sub 2 is equal to 0. Simplifying this a little bit, we end up with 2x sub 1 is equal to -x sub 2. And so we can deduce from here that the corresponding eigenvector is going to be 1 and -2. I'm just picking the two most simple numbers that I can think of. Not to mention, I'm also trying to match up my number choices with what we have in the answer choices here. You can see that each of these vectors have a 1 and a 2, or a 1 and a -2. And so from here, another thing we can do is we can also eliminate some answer choices. So going off this eigenvector computation, it would actually, you can deduce that it would be impossible to end up with an eigenvector of 1 and 2. And so there's because 1 and 2, when you plug those numbers into this expression, it won't satisfy this expression. So we can eliminate C and E, or no, we can eliminate B and E right away from our answer choices, and then go from there. So now this is where things are going to get a little different from the normal case of when you're using the eigenvalue method, because we need to come up with two linearly independent solutions we need to come up with two linearly independent solutions that satisfy the expression of x prime is equal to ax. And so that's the reason why what you'll notice in these answer choices, there's a t somewhere in all of those vectors, because there's a process involved that you need to do that involves t that satisfies x prime is equal to ax. So I'm gonna put that in, like, I'll revisit that. So what you're gonna want to do is, this time, to find our second linearly independent solution, we're gonna want to come up with another vector. And except the difference is where it follows a similar process to where we found our initial eigenvector. So you're gonna set up an equation like this. So let's just say, using the same eigenvalue of -4, -2, -1, 4, and 2 times x sub 1 and x sub 2. But instead of setting this equal to the 0 vector, we're going to set this equal to our previously generated eigenvector of 1 and -2, and then follow the same process of picking two numbers for x sub 1 and x sub 2 that satisfy this equation. And so doing that, I'll use I'll use the bottom row again. Doesn't really matter, but we can say that, yeah, we can say that 4x sub 1 plus 2x sub 2 is going to be equal to negative 2. And then simplifying this expression a little bit, we can say that we can say that 2 times x sub 1 plus x sub 2 is going to be equal to negative 1. And then let me get my computer to stop acting up again. Okay, cool. And so from here, yeah, it's just picking two numbers for x sub 1 and x sub 2 that satisfies this expression. Now, I mentioned that in the previous case, you want to pick two numbers that aren't 0 and 0. In this case, that doesn't mean that you can't use 0 as one of your numbers. As long as both of your numbers aren't 0, then you should be fine. So just to keep things simple, I'm going to use, let's just use I'm going to use 0 for x sub 1, and and that's going to make x sub 2 negative 1 by default. And so the next thing we have to do from here is now we have to come up with our solutions. So our first linearly independent solution, that's simple. That's the same process as in a normal case of normal eigenvalues, where you just have a constant times e to its eigenvalue of negative 4t times its corresponding eigenvector of 1 and negative 2. The process for setting up our second linearly independent solution is going to be a little bit different. So what we have to do is we're going to have another constant, so c sub 2 times e to the negative 4t again. But this time what we're going to do is we're going to use the previous eigenvector we had of 1 and negative 2, and then we're going to multiply that by t, and then add this new vector that we came up with here to it. So you should end up with something that looks like this. And then we can simplify this a little bit, and we'll end up with a solution that looks like e to the negative 4t of t, and then negative 2t minus 1. And now we have two linearly independent solutions. Now, you might be thinking, the reason why we have to you might be wondering why we have to do all this t stuff. The reason why is because if to anyone who's more extra perceptive, you might notice like this vector is already going to be linearly independent with that vector. So yeah, those two vectors they're going to be linearly independent. The problem is on its own, even though they're independent, it doesn't satisfy our initial constraint, that being that we have to satisfy x prime, where we have to satisfy the case of x prime is equal to ax. That's why we need to add this t stuff. That's what allows us to ultimately satisfy this expression. And so we need linear independence as well as satisfying this expression. So that's why you have to do all that t stuff as well. And so from here, let's come up with our general solution. So we can say that x sub t is going to be equal to c sub 1 times e to the negative 4t, e to the negative 4t times 1 and negative 2, plus our second linear. Let me move this down so because it's getting a little sloppy. Okay, and wait, yeah, okay. And then adding our second linearly independent solution to the end, we end up with c sub 2 times e to the negative 4t times its corresponding eigenvector, or vector of negative 2t minus 1. So now we can start to compare this with our answer choices. And looking at these answer choices, this matches up closely the most with answer choice C. And we can see that because looking at this term here, and this term, it's the same. It's just the negative 1 is in front of the negative 2, whereas I have the negative 2 in front of the negative 1. But it ends up being equivalent as a result, if you can see that. And so yeah, and this is nice because sometimes in questions like this, there might be a situation where they came up with a different vector. Like I came up with 0 and negative 1, and sometimes like the question they might choose different numbers that are also valid. And so it could create a little bit of a headache because you have to decipher the answers and see which one is equivalent by plugging in the numbers back into this expression and making sure that it matches up, if that makes sense. But thankfully in this case we don't have to do that because our answer was able to match up perfectly. So yeah, so the answer to this question, if I'm not mistaken, is going to be C. And then also let me clean this up a little bit because I feel like this 4 is a little sloppy. And then this 2 is also a little sloppy, so let's clean this up a little bit. Okay, cool. So yeah, so the answer to this question is going to be C. Okay, so this question we are dealing with the first case of an inhomogeneous system of differential equations rather than just a single inhomogeneous equation. And so as a result, our general solution is going to take up a little bit of a different form from the homogeneous case of just x prime is equal to ax. Because now we have this additional term here, let's just call it x of t or something. And so as a result, similar to the case of a single inhomogeneous differential equation, our general solution is now going to take the form of x of t is going to be equal to x sub c of t plus another term x sub p of t, where x sub p of t would be our particular solution that handles the inhomogeneous part of the differential equation. And then this x sub c of t, that's just the same process as a normal homogeneous system, where you'd use the eigenvalue method to come up with your two terms and attach some eigenvectors to that. And similar to the case of a single inhomogeneous differential equation, when you want to use the method of undetermined coefficients to find your particular solution, you're still going to have to find your complementary solution, because you're going to need to compare your initial guess with that complementary solution to make sure you don't have any conflicting terms. But the cool thing is we don't have to find the eigenvectors, so that saves us a little bit of time on the computation. You just have to find a general form of the complementary solution. That will give you enough information to check for conflicts. So I'll do that. So just finding the eigenvalues. Yeah, pretty much in this case, you only have to find the eigenvalues for the general solution. So setting up the determinant for that, we end up with 2 minus lambda, negative 1, 6, negative 3 minus lambda is equal to 0. Oh, also, similar to another question that dealt with undetermined coefficients on this exam, I'm going to rush through the complementary solution computation because if you're not comfortable with that, I would suggest practicing some cases of solving a system of homogeneous differential equations to get comfortable with the complementary solution, because I mostly want to focus on the particular solution for this question. So I'm going to assume that that people who are watching this question are familiar with the case of just x prime is equal to ax. So continuing further, we end up with 2 minus lambda times negative 3 minus lambda plus 6 is equal to 0, and then this simplifies to just this is going to simplify to lambda squared plus lambda is equal to 0, and then that gives us lambda values of 0 and negative 1. So our complementary solution is going to take up the form of x sub c of t is equal to c sub 1 times some eigenvector plus c sub 2 times e to the negative t times some other eigenvector. So I'll just call these v sub 1 and v sub 2. I know those kind of look like U's, but yeah, those are V's. Sorry about that. My handwriting is not the best. I'm one of those people where my U's and V's don't look they look very similar. So, yeah, okay, that I digress. Anyway, so now we can focus on our particular solution. And so for that, since we're using the method of undetermined coefficients, we're going to have to come up with an initial guess and then go from there. Come up with our initial guess, see if there's any conflicting terms. If there are, then change up our guess and keep doing that until we don't have any conflicting terms. So for my initial guess, I'm going to say that x sub p of t is going to be equal to just a and b. And the reason why my guess looks like this is because focusing on the inhomogeneous part of our system here, you can see that we just have a constant vector because it's just 0 and 1. And so similar to the case of method of undetermined coefficients for a single differential equation, when you just see a constant term in your inhomogeneous part, your guess is also just going to be a constant. But in this case, we're dealing with a vector, but we're dealing with a vector instead of a scalar, so we're going to end up with multiple terms. So I put a and b there because there's two constants here. So that's why my guess looks like that. And then comparing that to our complementary solution, we can see that we do in fact have a conflict. You can see we have a conflict here, because this is also just a constant vector. And so as a result, our guess is not going to be linearly independent with our complementary solution. So we're also going to have to attach a t to this. Now, the next thing we have to do is we need to add another constant vector, that being just here, so c and d or something like that. And the reason for this is actually because You might be thinking, because in the case of a just a single differential equation where you're just using like the scalar version of method of undetermined coefficients, usually just attaching a t to this term would be enough to get rid of the conflict. But what's actually happening behind the scenes is what you really should be doing is you need to add another constant term. They just don't mention that because that constant term is going to end up combining with this constant term. Um, and that's okay because they can be linearly combined, if that makes sense. It's kind of like, I guess another way you can look at it is like it's not this isn't the best analogy, but one way I like to look at it for the case of like the vector version of undetermined coefficients, usually like let's say we had like a differential equation that looks like, I don't know, y double prime plus y prime plus y is equal to, let's just say like 3 times x e to the 3x. Usually we know that in this case, like when you're trying to come up with your guess using undetermined coefficients, you'd say that x sub p of t, or no, or y sub p of t, or y sub p of x, y sub p of x would just be equal to ax times e to the 3x plus b times e to the 3x. You can see how we have two terms there because of this x here. In the case of this case, after I added this t, we also have to add the constant for a similar reason to the reason why we added this term here. It's not the best analogy, but that's the best. I'd say that's like, yeah, that's kind of a good way to look at it. That's kind of why it differs from the case of a single differential equation when you're using the scalar version of method of undetermined coefficients. So yeah, so anyway, yeah, so as a result, this is going to be our final guess of, or our final trial solution, appropriate form of the trial solution. So we can compare this with our answer choices and we can see that it matches up with E. So yeah, so the answer to this question is going to be E. All right, so this is going to be the first question on this exam that deals with Laplace transforms. So in this case, it's asking us to find the inverse Laplace transform of f of s. And so to start, in this case, well, we have a fraction in our hands that looks kind of ugly at first. So right off the bat, I know right away we're going to have to do a little bit of a partial fraction decomposition on f of s here in order to find the inverse Laplace transform. Because the goal is you want to use a partial fraction decomposition to break up the original function into smaller parts that resemble things that you can kind of match up with things on your table of Laplace transforms. Because that's what the process of finding the inverse of a Laplace transform would entail. If you want, unrelated, but if you wanted to find an inverse Laplace transform manually, that would involve complex analysis. So yeah, just stick with the table for this. So yeah, to start, let's split up this. Let's split this up a little bit. And so to start, the first thing I'm going to do is I'm going to factor out the denominator, because with partial fraction decompositions, you want to split up the two things you have to do beforehand. You have to make sure that the highest power of your denominator is greater than the highest power of your numerator. Because if it's not, then you're going to have to do a little bit of long division beforehand before doing the partial fraction decomposition. Cool thing about this question is we don't have to do that because we can see that the highest power of the denominator in this case is 2, and then the highest power of the numerator is 1. So we don't have to do that. And then the next thing you have to do is you want to try to split up the denominator as much as you can and then do your partial fraction decomposition, because that's the only way you could end up with like a meaningful decomposition. So to start, we can split this up into s plus 1 over s plus 1/2 times s plus 1/2. Now, usually, generally speaking, in situations like this, your partial fraction decomposition would look something like a over s plus 1/2 plus b over s plus 1/2 or something like that, right? The problem is, in this case, since these two terms are identical, the decomposition is actually going to look a little bit different because of the fact that they're duplicates. So I'm actually going to rewrite this as s plus 1 over s plus 1/2 squared. And so as a result, our partial fraction decomposition is going to look like a over s plus 1/2 plus b over s plus 1/2 squared. So basically, in the case of when you have a duplicate, your decomposition, you have to set up the amount of terms equal to the amount of duplicates you have So we have a pair, so two s plus 1/2 terms. So we're going to end up with two terms, like the normal case. But with each term, you have to increment the exponent of the denominator by 1. So starting with the first power and then going up to the second power. And so this is why the decomposition is going to end up looking like this. So now that we have our decomposition, now we can start focusing. We split this up as much as we can. So now we can start to solve for a and b, and then once we have an a and b value, then we can start to do our inverse Laplace transform. So to do that, recall that in this case, in order to solve for a and b, you want to set up an expression where you multiply each of these terms. So each of these terms by your original expression, multiplying it by the denominator. And so when you do that, you should end up with an expression that takes the form of a times s plus 1/2 plus b is equal to just s plus 1. And the reason why it looks like this is because when we distributed this term with these things and everything here, this is going to cancel out, and then this is also going to cancel out when you simplify everything out, and so you end up with something that looks like this. And so now what I like to do in situations like this is there's one of two ways you can start to find a and b from here. If you remember anything from how to do a partial fraction decomposition, you can either set up like a test value for s that allows you to cancel out one of your letters, that'll allow you to just solve for a single letter. Like in this case, you can see here we have an a times an s plus 1/2. So if we set s, if we use a test value saying that s is equal to negative 1/2, then we can cancel out a, and so we can end up with a times 0 plus b is just equal to negative 1/2 plus 1. And then simplifying this down, we can find right away that b is going to be equal to just 1/2. And then from there, then the next thing you can do, if you can't do that, if you can't set up a test value, the next thing you can do is you can distribute out this expression. So I can distribute and end up with as plus 1/2 a plus b is equal to s plus 1, and then set up a couple of equations that relate like terms. So what I mean by that is, by like terms, I mean we have an as here and we have an s here. So those would be like terms. So we can say that a would be equal to just 1 because it's a 1 times s. And then another case of like terms, we have just 1/2 a and b, and then this 1. And so we can say that 1/2 a plus b is going to be equal to 1 as well, and then solve for things. But going off here, we were able to find right away that a is equal to 1. So we have our two values for a and b. So we can plug those things back into this expression, and we're going to end up with a completed partial fraction decomposition, which I'm going to write over here. I'm going to write that as, we can say that s plus 1 over s squared plus s plus 1/4, so our original expression of f of s, is going to be equal to 1 over s plus 1/2 plus 1/2 times 1 over s plus 1/2 squared. And so now that we've done this, now we can start computing the inverse Laplace transform. So we can say that the inverse of f of s, we can say that that's going to be equal to the inverse Laplace transform of this expression. So I'll just write that over here. So we can say that that's going to be equal to 1 over s plus 1/2 plus 1/2 times 1 over s plus 1/2 squared. And then the next thing we can do is, now that we've broken this up into smaller parts, we can find the inverse Laplace transform of these two components individually. So I'm going to rewrite this actually, as we can say that the inverse Laplace transform of f of s is going to be equal to the inverse Laplace transform of 1 over s plus 1/2 plus the inverse Laplace transform of, and then another thing is we can get rid of constants. Basically, let me rephrase. When it comes to splitting up your inverse Laplace transform, it's similar to when you're splitting up an integral into smaller parts, where you take out your constants and split it up into smaller integrals and evaluate each of the parts individually. So we have a constant here. So we can take that out of the inverse Laplace transform and say that the inverse Laplace transform is equal to the inverse Laplace of this plus the inverse Laplace transform of 1/2, or wait, yeah, 1/2 1/2 times the inverse Laplace transform of 1 over 1 plus, or s plus 1/2 squared, like this. And so now that we've split it up as much as we can, now we can start to evaluate our inverse Laplace transforms and just start comparing to the table. So here you can, if we refer to our table, we can see that this term, this is reminiscent of the term of 1 over s minus a. And we know that this is going to be the general form of the Laplace transform of the Laplace transform of e to the at. And so you can see how it matches up, because if we compare this with this term, you can see that a is going to be equal to negative 1/2. And so that's one of the inverses out of the way. So this is going to just become e to the negative 1/2 t. And then now we can focus on this term over here. And so if we refer back to our table of Laplace transforms, we can see that this term, that's reminiscent of the form of something that takes the form of n factorial. So n factorial over, that's going to be s minus a times n plus 1. And so from here, we can see that this n plus 1 is going to match up with this 2. And so we can say that n plus 1 is going to be equal to 2, which means that n is going to be equal to 1. And then similar to the first part, we can say that a, that's just going to be equal to negative 1/2. And then it's n factorial because we know that n is 1 and 1 factorial is 1. So yeah, and then we can deduce again that a is going to be equal to negative 1/2. And then this thing that we got from the table of Laplace transforms, we know that that's going to be the general form of the Laplace transform of t to the n times e to the at. And so now we can evaluate this inverse Laplace transform, and this is going to go to t squared, or no, just t, because n is 1. So t times e to the negative 1/2 t. And so now that we've evaluated those inverse Laplace transforms, let me move these things out of the way. So let's clean this up a little bit, because yeah, this got a little sloppy. Let's move this, I'll move this up here. And then now we can finally say that the inverse of f of s is ultimately going to be equal to e to the negative 1/2 t plus 1/2 times t times e to the negative 1/2 t. And so now we've completed the inverse Laplace transform of f of s. And so yeah, so this is going to ultimately be equal to the Laplace inverse. That's a sloppy L. Yeah, we can finally ultimately say that this is going to be equal to the, forget it, forget it. That's just going to be f of s. So yeah, and so yeah, so now we can compare this with our answer choices, and matching this up, this matches up the closest with answer choice C, because yeah, where the only difference is that they just put the t with the 1/2 over there, if that makes sense. So yeah, so the answer to this question is going to be, yeah, it's going to be C. Okay, so in this question we're dealing with another initial value problem, but this time I'm going to solve this initial value problem using Laplace transforms. Part of the reason why I'm going to do that is, well, we couldn't really do it the normal way anyway, because on the right side you can see here that we have a Dirac delta function. And so as a result, it's going to make things a little more interesting for us here. So to start, in order to solve an initial value problem using Laplace transforms, you're going to want to take the Laplace transform of the given differential equation here, and then from there take an inverse, and it will give you the solution to the IVP. So starting from left to right, we have a y double prime. So since we have a second derivative, going to your Laplace transform table, that Laplace transform is going to translate into something that takes the form of capital Y of s minus our y of 0 value times s, so just 0 times s, minus our y prime value of 0, which is also just 0. And then for our second term, we have a 2y prime, so that's going to turn into, oh, and then I forgot an s squared here as well. And then here for the second term we have a 2s capital Y of s minus the term minus the initial value of y of 0 again, which is going to be 0. So just so minus 0 again. And then for the third term we have a 5 of y, so that's just going to turn into 5 capital Y of s. And then on the right side we have a Dirac delta function. And so recall that looking at your Laplace table, the Laplace transform of a Dirac delta function is going to take the form of e to the negative cs, or c is going to be this value over here. And so this doing a Laplace transform, we're going to end up with e to the negative 5s. And then we can simplify this a little bit because we have a lot of zeros, because the next thing we want to do is we want to isolate this capital Y of s so that we can take a Laplace inverse that will give us a solution. So after simplifying things down a little bit, you should end up with something that takes the form of capital Y, or that's a v, capital Y of s times s squared plus 2s plus 5 is equal to e to the negative 5s. And then since we want to isolate y of s, you'll ultimately end up with the fraction that takes the form of y of s is going to be equal to e to the negative 5s over s squared plus 2s plus 5. And so now we have it in a form where we can take a Laplace inverse. So our goal is, next thing we have to do is we need to find the Laplace inverse of y of s. And so to start, usually when you're solving an initial value problem using Laplace transforms, more often than not, you're going to end up with a starting term that looks pretty hideous like this, where it doesn't nicely mesh with anything on your Laplace table. So you're going to have to manipulate and mold your form a little bit into something that matches up with something on the table. And there's a variety of ways you can do that, whether it's by splitting up this polynomial using a partial fraction decomposition, or completing the square to make it get closer to like a form of something. And also another thing we have to note here is that we have an e to the negative 5s term there. And so as a result, when we take our inverse, the next thing we're going to have to do is we're also going to need to apply a unit step function at the end after we do our Laplace inverse, or to account for a shift of some sort. And so looking at this polynomial down here, I can't really factor it, so my next idea of what I would want to do is to complete the square. And then also I'm going to isolate this e to the negative 5s and come back to that later, since that's not going to affect anything until the very end. So we can say that y of s, after completing the square, we can turn this into something that's equal to e to the negative 5s times 1 over s squared plus 2s plus 1 plus 4, which is going to be equal to 1 over s plus 1 squared plus 4. And I'll bring this term back later. I'll write that at the very end. And so now you can see that this is going to be closer to the form, if we go to our Laplace table, this is going to be closer to the form of, it's going to be closer to the form of case number 9 down here. So e to the Laplace transform of e to the at times sine of bt. You can see how it kind of resembles this form. So let me write that over here. That's the form that I'm going to be working towards. So let me write that over there. So I'm going to be working towards the case of the Laplace transform of e to the at times sine of bt is equal to, it's going to be equal to b over s minus a squared plus b squared. That's the form that I'm going to be working towards. So we can see that we have our b term as well as our a term taken care of. You can clearly see here that a is going to be equal to -1, and then b is going to be equal to 2. The problem is we do need to deal with this 1 in the denominator, since our Laplace transform calls for a b in the denominator, and we know that b is equal to 2. We're going to have to change this up a little bit so that we can have a 2 in the numerator as well. So what I'm going to do is I'm going to replace this 1 with a 2, and then multiply the entire thing by 1/2, because that will give us an equivalent expression that also fits in with our general form of the Laplace transform we want here. And so I'm going to rewriting this, we should end up with something that's equal to 1/2 times 2 over s plus 1 squared plus 4. So now you can more clearly see, if with this isolated, let me also put this in parentheses to make it more obvious. Now we can see that this thing in parentheses is in the form of what we want here. And so from here we can take our Laplace inverse, and that's going to give us a form of 1/2 times e to the negative t times sine of 2t. And also, since this 1/2 is a constant, I was able to just take it out and then put it back in later, because it's similar to when you're solving an integral, where you can take out your constants if you want to make your life easier, and then evaluate the integral and then put the constant back in at the very end. So that's the same thing that I did over here. So now going back to this e to the negative 5s term there, that is going to, because of that term, we're going to have to apply a unit step function and shift this a little bit. And so we can see that we have a e to the negative 5s term. And so as a result, since we know that c is equal to negative 5, let me write that over here. We know that c is equal to negative 5. And c is equal to negative 5. We need to replace each t term in our function. So each t term with a t minus 5. And then I made a mistake. C is supposed to be positive 5, not 5. So what we need to do is we need to replace each t term with a t minus c. And so we're gonna, in this case, we're gonna have to replace each t with a t minus 5. And so this is going to turn into 1/2 times e to the negative t minus 5 times sine of 2t minus 5. And then that shift will take care of this e to the negative 5s term that we had originally in our Laplace, or in our y of s term before we took our Laplace inverse. And so yeah, so now we have this, and then this, after we've done this inverse, we have effectively solved the initial value problem. And this should be our answer. So now we can compare this with something in our answer choices. And that matches up closely with answer choice D, I believe. If I didn't, yeah. Okay, yeah, cool, yeah. So the answer to this question is going to be D. Okay, so in this question, we are going to be, it's asking us to find the Laplace transform of a function. So find f of s of f of t. And recall that in order to do that, there's two ways you can do that. You can either use the formula of a Laplace transform, where the Laplace transform of f of t is going to be equal to the integral from 0 to infinity of e to the negative st times f of t dt, and that will give you the Laplace transform. So this would be equal to f of s. Now for this, or the other thing you can do is also the more normal approach of using the table of Laplace transforms that is conveniently given to us on this exam. For this question in particular, I especially would not recommend trying to find the Laplace transform manually, because we're given a pretty ugly function here. I just put this here because I just put the formula here because you can manually compute it as a last resort if you don't know how to use a Laplace transform table, but I wouldn't recommend it. Try to familiarize yourself with the Laplace transform table, especially for a question like this, because if you try to find the Laplace transform of this function manually, you're not going to have a fun time. You might even cry. So yeah, don't do that. Okay, anyway, yeah, let me pretend I didn't even put this here, just to discourage you from trying to find this manually. So anyway, the first thing I'm going to do is we have to decipher this function a little bit, because since we don't have a simple function on our hands, we can't just simply compare this to one of the cases on the Laplace transform table. We have to decipher a little bit, break it up into smaller pieces before we can do that. The reason I know that is because you can see we have a sine 3t term. If it was just this, then yes, you can compare it to the sine case on your Laplace transform table, and then just find the Laplace transform. But we also have a t term here, and so that's going to change things up a little bit. So the first thing I'm going to do is I'm going to decipher this and say that f of t is going to be equal to 2 times the parentheses of t sine of 3t. And the reason why I'm isolating the 2, when you're handling Laplace transforms and inverse Laplace transforms, it's similar to when you're evaluating an integral, where sometimes if it's easier for you, you can make your life easier sometimes by taking the constant out of the integrand and then evaluating the integral without the constant and then putting the constant back in afterwards. A similar that idea is also applicable to Laplace transforms. And so that's why I took out the t, because now you can more clearly see that we're dealing with a case where now our function takes the form of, looking at our Laplace transform table here, it resembles this case at the very bottom. So scenario number 19 here of t to the n times f of t. I know that the question says that f of t is equal to 2t sine of 3t, but in reality, the way you should look at this question is that f of t is actually just going to be this sine of 3t term. So this is going to be f of t. And then we have this t here. So now you can more clearly see that this resembles the form of the case of, I'll write this here, so t to the n times sine of at. Or yeah, t to the n times f of t, where f of t is equal to sine of 3t. And so we know that in that case, the Laplace transform of t to the n times f of t, that's going to be equal to -1 times n times the nth derivative of the Laplace transform of our f of t. So I'll denote that like this. And the reason I know that it's a derivative is because you can see, notice how I put the n in parentheses here. When you see an exponent in parentheses like that, that means that it's going to be a derivative rather than just an exponent. And you might have even seen it in other questions. Like you might be dealing with a differential equation, and it gives you a derivative that's beyond like the second or third derivative. And instead of writing like y quadruple prime or something, they wrote it as y to just parentheses 4. It's just a derivative. So the nth derivative of the Laplace transform of f of t, so just this sine of 3t thing. So let me organize things a little bit. So in this case, we can say that the Laplace transform of t times sine of 3t is going to be equal to, -1 to the first power, because we know that n is just equal to 1 since it's just a t, times the first derivative of the Laplace transform of sine of 3t. So let's just say ds of the Laplace transform of sine of 3t. And so now that we have that set up, now we can ultimately find our Laplace transform. Then I can clean up that closing bracket a little bit. Okay, cool. So now that we have that, going back to our Laplace table, now we can look at the scenario for just sine of at. So we know that the Laplace transform of sine of at, that's going to be equal to a over s squared plus a squared. So let me write that down here. We know that the Laplace transform of sine of at is equal to a over s squared plus a squared. So translating that to our case, we can say that the Laplace transform of sine of 3t is going to be equal to 3 over s squared plus 3 squared, which is 9. So now that we have that, now we need to find the derivative of that. So moving this down here, we can ultimately say that the Laplace transform, messed up there. We can ultimately say that the Laplace transform of t sine of 3t is going to be equal to -1 times the derivative of this. So I'm going to say that this is equal to f of s. So we need to find f prime of s. So that's just, we can just use quotient rule for that. So you should end up with a derivative that takes the form of -3 times 2s over s squared plus 9 squared. And then I can clean up that s a little bit. So you should end up with a final and then the next thing we have to do, don't forget, I took a constant out here, so we have to bring that constant back in. So multiply this entire thing times 2. And then we can simplify this, and this is going to simplify to just 12s over s squared plus 9 squared. And so this is going to be the Laplace transform of f of t. So this is ultimately going to be the answer to this question. And so, yeah, so comparing that with our answer choices, we can see that the answer to this question is going to be A. Yeah. Okay, so in this question, we're dealing with another Laplace transform, or it's asking us to find a Laplace transform, but we're dealing with a piecewise function. And so as a result, our initial setup process is going to be a little bit different from the normal case of when you're just doing a Laplace transform of a normal function that stays the same all the time. And that's going to change up your approach no matter how you do this. So if you like to brute force your Laplace transforms and use the formula, then you'd have to split this up into two integrals since we have two parts of our piecewise function, that being 1 and t squared. And then if you were to do it the normal way, I guess you could say the conventional way of using a Laplace transform table, if you're not insane. No, I'm kidding. That would be you'd have to combine this and mash it into one big function using unit step functions. And so to start, your integral, if you're going to do it that way, your integral would end up looking like the Laplace transform of f of t is going to be equal to the integral from 0 to 2 of 1 times e to the negative st plus the integral from 2 to infinity of t squared times e to the negative st. And then now, if you were to use a Laplace table and turn this into one big function, to start, let me write out a table here, or no, let me write out a graph here to give you an idea of what I'm talking about. So we're dealing with a piecewise function, and we know that, as written here, f of t is defined as 1 from 0 to 2. So from 0 to like 2, somewhere around here, then f of t would just be a flat line. Let's just say this is 1 from 0 to 2. And then beyond 2, f of t is defined as t squared as written here. And so then this flat line would turn off and then turn into something that maybe looks like this or something like that. And so the way unit step functions work is it's like effectively like you're adding a couple of toggle switches where you like one part of the function turns on between an interval, and then at the end of that interval it turns off, and then the next part of that interval turns on, if that makes sense. And so to start writing out our big function, we can say that f of t, using unit step functions, starting at 0, I'm going to start at 0 and work our way up through the intervals. We can attach a unit step function to 1 because we know that this 1 portion turns on at 0. So u of t minus 0 times 1. And that's going to be a positive 1 because it's turning on. So I'm going to use a positive to represent turning on, and I'm going to use a negative to represent turning off. And so we know that it turns off at t is equal to 2. So then we'd add a unit step function of u of t minus 2 to account for that shift times negative 1. And then we know that this function of t squared that turns on at t is equal to 2. So using the same unit step function of t minus 2, we can say that this is just going to be positive t squared. Similarly, if we had like a third term where we had a third part of the piecewise function beyond this term, then when this turns off, then we'd have to let me put in a hypothetical. Let's say we had like a third case of like where f of t is defined as like t cubed. Let's say this is like we have like a 5 here or something, and then it's defined as t cubed beyond 5. So like this or something. Then in that case, then this, to represent this turning off, I'd use a negative t squared. So then we'd end up with like u of t minus 5 of negative t squared, like this. And then this interval would turn on. And so yeah, that's the way unit step functions work when you're mashing up your piecewise function into one big function. And so then we can further reduce this. So looking at this first term, that's just a unit step function of t minus 0. So that's a pointless step function that represents 0 shift. Not to mention the fact that this is just a 1. So this first term, we can simplify that to f of t is just equal to 1. And then we have the same unit step function here and here, so we can merge this into one big term, and we'd end up with 1 plus our unit step function of u of t minus 2 times t squared minus 1. And so now at this point, now we can take our Laplace transform. And so since we're dealing with a unit step function, let's write this out. So we can say that now we can find the Laplace transform of f of t. And since we're dealing with a case of two terms, by linearity of Laplace transforms, we'd have to break this up into two smaller Laplace transforms. So the Laplace transform of f of t, that's going to be equal to the Laplace transform of 1 plus the Laplace transform of u of t minus 2 times t squared minus 1. So now focusing on the Laplace transform of 1, that's trivial. Looking at your Laplace transform table, that's the constant case. So that Laplace transform is just going to be equal to the constant divided by s. So this is going to go to just 1 over s. And then in this case, we're dealing with a unit step function attached to a function. And so what that's going to end up looking like is, well, we need to distribute this shift into our function, which will allow us to get rid of this term from our term, I guess. And that Laplace transform is going to end up looking like where you have, that's going to be the case of e to the negative cs times the Laplace transform of the function, let's just say f of t, with the shift accounted for. So that's going to end up being like f of t plus c, like this. The reason why so be careful here, because notice how I put a plus here instead of a minus. You might think, oh, we can just put this t minus 2. We can replace this t with a t minus 2, but we're actually going to have to replace it with a t plus 2 because we're shifting upwards or to the right in our graph. And so as a result, putting in the terms, we know that that's going to be c. And so then this Laplace transform is going to end up turning into e to the negative 2s times the Laplace transform of t plus 2 squared minus 1. And back to what I mentioned about the linearity of Laplace transforms, we're going to have to break this up into smaller parts since we're dealing with addition and subtraction. And we'd have to multiply this out to turn it into its individual parts. So when you do that, we can say that t plus 2 squared minus 1, that can be multiplied out to t squared plus 4t plus 3. And so then the Laplace transform is going to end up taking the form of, that's going to then turn into the term of 1 over s plus e to the negative 2s times the Laplace transform of t squared plus 4 times the Laplace transform of t. I'm taking out the constants here, by the way, plus the Laplace transform of 3. And then from here, we can just compare each of these three cases to our Laplace table. And so looking at the first case, that's going to correspond to this scenario over here, scenario 3, so t to the n. We know that n is going to be 2 here, so this is going to turn into 2 over s cubed. And then here, this is the same case as this case, except it's just 1 power lower, so that's going to turn into 4 times 1 over s squared, which just simplifies to 4 over s squared. And then this final term, that's just a constant, so that's going to be trivial. So that's going to just turn into 3 over s. And so as a result, our final Laplace transform is going to take the form of f of s is going to be equal to, or no, not equivalent, oops. That's going to be equal to 1 over s plus e to the negative 2s times 2 over s cubed plus 4 over s squared plus 3 over s. And so so that should be your final answer. And so comparing that with our answer choices, then we can see that the answer to this question is going to be B. All right, last question on this finally. No, I'm kidding. Okay, anyway, so we have another initial value problem. And so in this case, for this initial value problem, I'm going to use a Laplace transform to solve it again, just like many of the previous questions around this part of the exam. The reason why is because, well, for one, we have a g of t term, an unknown function. So we can't really use a normal approach to solving this initial value problem, even if we wanted to. Not to mention, you can see in each of these answer choices, each of them have this integral in them that resembles the form of a formula for a convolution. And so as a result, yeah, we're going to have to use a Laplace transform to solve this one. So going from left to right, the Laplace transform of y double prime in this case, if you look at your Laplace table, that's going to end up being s squared times capital Y of s minus our first initial condition of y of 0 is equal to 2 multiplied by s, and then our other initial condition of y prime of 0 is equal to negative 4, so that's just going to become a plus 4. And then our next term, we have a 3y prime. So the Laplace transform of that is going to end up looking like this, where we have to take out the constant first. Make sure that you do that, because that you can end up having some conversion errors if you keep that 3 in, and then you'll end up with a completely out of whack answer. So taking out the constant, you should end up with a Laplace transform of 3 times parentheses s of capital Y of s minus 2. And then I didn't include an s with this 2 this time because this s is to a first power. And so each subsequent term that you add to the Laplace transform of a derivative, your next s power goes down in a power. It goes down by 1 with each pass. So it just becomes s to the 0, which is just 1. And then for our last term, we have 2y, so that's going to be 2, that's just going to turn into 2 times the capital Y of s. And then the Laplace transform of our unknown function g of t, that's just going to become capital G of s. And then from there, we can simplify this equation a little bit, because the whole goal with solving an initial value problem using Laplace transforms is we want to take the Laplace transform of the differential equation, and then we want to find a new term from that, and then take the Laplace inverse of that, and that'll give us a solution to this problem. And the term that we want a term of just y of s. So we want to isolate y of s. So when we do some simplifications, you'll end up with after combining like terms and distributing things a little bit, you should end up with s squared times capital Y of s minus 2s plus 4 plus 3s capital Y of s minus 6 plus 2 capital Y of s. And then that can simplify again, taking out the y of s. You can end up with capital Y of s times s squared plus 3s plus 2 minus 2s minus 2 is equal to g of s. And then we can finally isolate y of s by moving these terms to the other side and then dividing this, and then you end up with y of s is going to be equal to g of s plus 2s plus 2 over s squared plus 3s plus 2. So now that we have y of s completely isolated, now we can start to take our Laplace inverse and come up with a solution. Usually what that entails is where you have to kind of manipulate the expression that we have here into something that fits in with some of the cases on your Laplace table. And usually that consists of like maybe doing some partial fraction decompositions, maybe completing a couple of squares, or maybe splitting this term up into smaller terms, or mixing and matching those processes. And in this case, we're going to have to do that because we have the Laplace transform of an unknown function here of g of s. And so we can't just take a partial fraction decomposition of this right away. We're actually going to have to split this up into two terms. Also, I mentioned at the beginning of the question that the answer choices each have an integral that looks like the formula of a convolution. That's also going to come into play as well because of our unknown function here. So the first thing I'm going to do is I'm going to split this up into two terms where we have g of s over s squared plus 3s plus 2 plus 2s plus 2 over s squared plus 3s plus 1. So now we have one term that can be split up with a partial fraction decomposition. And then this term can also be split up, but we're gonna have to take one more step and then we'll be able to get there. So going back to the thing about convolutions. So we know that we have the unknown function g of t and its Laplace transform g of s. And we also know that the formula for a convolution of two functions, let me just write that over here. We know that let's just say f of t and g of t. Let's just say f of t and g of t. F of t convoluted with g of t that's going to be equal to the integral from 0 to t of f of tau times g of t minus tau with respect to tau. And then the next thing we have to do, and then we have to relate this to Laplace transforms. The way Laplace transforms work with convolutions, we can say that the Laplace transform of f of t convoluted with g of t, if you look at your Laplace table, that's going to tell you that it's equal to the Laplace transform of f of t times the Laplace transform of g of t. So that would look like the Laplace transform of f of t times the Laplace transform of g of t. And then that's just going to be equal to f of s times g of s. So we can simplify that a little bit. Yeah, we can just say that the Laplace transform of f convoluted with g is just going to be f of s times g of s. And then from here, the next thing you can do is we have a g of s term. It's this unknown function here. And now we just have to come up with a hypothetical f of s, and then we can go backwards and end up with a solution. So to do that, what you can do next is you can split this up into something that takes the form of just g of s times 1 over s squared plus 3s plus 2. And then we can take this split up term and call this our hypothetical f of s. So that's what I'll do, calling that f of s. And then from here, now you can see that we have the case of just f of s times g of s. And then we can take the inverse of that, and that's going to give us a convolution for our general solution. And so now for that process, since we have to go backwards, we still have to find the Laplace inverse of f of s. The Laplace inverse of g of s, that's simple. That's just going to go back to g of t. But yeah, we still need to find the Laplace inverse of f of s. So what that's going to look like is we're going to have to take a partial fraction decomposition of that. So that's what this is going to turn into. And then let me clean this up a little bit. I'm going to keep this labeled as f of s, but keep that kind of out of the way. So I'll just put it like here or something. And so then this term can turn into g of s, or actually, you know what? I'll bring the g of s term down later. I'm just going to focus on the f of s term right now. We can factor this s squared plus 3s plus 2 into just 1 over s plus 1 and s plus 2. And then that's going to be equal to, with our decomposition, a over s plus 1 plus b over s plus 2. And then we can move on and then to continue with our partial fraction decomposition, the next thing we'd have to do is multiply each of these terms by our denominator. So distribute this term with all three of these terms. And then you should end up with something that takes the form of an equation that looks like a over s plus 2 plus b over s plus 1 is going to be equal to 1. And then all we have to do from here is solve for a and b. And there's two ways you can do that. You can either relate the like terms together and then set up a system of equations, or you can come up with a couple of test variables for s and cancel out something else and solve for the letters one at a time, if that makes sense. I think for this situation, it's going to be easier to do that. So we can start with a test s value of s is equal to -1. That's going to cancel out b. And so you'd end up with an equation of a times 1 plus b times 0 is equal to 1. And then we can say that a is just going to be equal to 1. And then for our next test variable, we can say s is equal to -2. And in that case, that's going to cancel out a, and you'd end up with a times 0 plus b times -1 is equal to 1. And then we can say that b is going to be equal to -1. So after completing that decomposition, then you'd end up with the term of g of s times 1 over s plus 1 minus 1 over s plus 2. And then now moving on to this term over here, it's going to follow a similar process of the same decomposition because we have the same denominator, except our terms are going to be different because the numerator is different. So when we split this up, you'll end up with the same decomposition of a over s plus 1 plus b over s plus 2 is equal to 2s plus 2 over s squared plus 3s plus 1. Actually, you know what? Let me use different letters to avoid confusion too. I'll just use c and d. And so, but our c and d values are going to be different from a and b because our numerator is different. And so the decomposition is going to end up being different, even though the initial form is going to be the same. So similar to the first case, I'll use the same test variable approach. So you'd end up with an equation that looks like c times s plus 2 plus d times s plus 1 is going to be equal to 2s plus 2. Using our first test value of s is equal to -1, then you end up with negative c is equal to 2 times -1 plus 2, which is going to just be equal to 0. Oh, and then I realized, no, it's positive c, not negative c. And then the next term is using the same test variable as last time. If s is equal to -2, then you'll end up with d, or negative d, or yeah, d times -1 is going to be equal to 2 times -2 plus 2, which is going to be negative d is equal to -2, so d is going to be equal to 2. And then that will give us a final term, cleaning this up a little bit. If we put d is equal to 2 over here, then we'll end up with a final term of g of s times this thing, and then plus 2 over s plus 2, because we know that c is equal to 0. So that's going to completely get rid of this term over here. And so from here, now we can take our Laplace inverse. We can just take the Laplace inverse of this, and that's going to be equal to the Laplace inverse of not f of s, capital Y of s. So, and then that will finally give us our solution to this question. And then by linearity of Laplace transforms, we'd have to split this up into two smaller Laplace inverses. That's the way you'd have to write it, technically speaking. But since we have a bunch of simple cases here, we can just look at each term and compare it to our Laplace table and just go from there. So to start, we know that the Laplace inverse of g of s, that's just going to go back to g of t. So that's just going to turn into a g of t. The next thing I'm going to do is, since we know that the Laplace transform of f convoluted with g is going to be equal to the Laplace transform. It's going to be equal to f of s times g of s. I'm going to write a convolution here, just like the convolution symbol, to represent that, and then I'm going to convert that into its formula later. But before that, let's also evaluate this term. So this is so this is going to go to, and then let me rewrite this as, let me put the g of s on the other side, so that it can translate more nicely into our convolution formula, because convolutions are not commutative the way multiplication is, and so the order does matter. So you'd end up with 1 over s plus 1 minus 1 over s plus 2 times g of s, and then this just goes to g of t, and then that's going to, looking at our Laplace table, each of these fractions, these are reminiscent of the case of when you're taking the Laplace transform of e to the at, and so this is going to turn into negative e to the negative 2t, and then this is going to turn into e to the negative t, like so. And then we can say that this is going to be convoluted with g of t. And then this term, that's just going to go to plus 2 times e to the negative 2t. Like so. Yeah. If I did everything correctly, yeah, that's what it should look like. So now we have found the solution. All we have to do now is turn this convolution into its integral formula. So that's finally going to, matching this up with our answer choices, that's finally going to ultimately turn into something that takes the form of like 2e to the negative 2t plus our integral over here. So looking back at the formula for a convolution, that's going to turn into the integral from 0 to t of f of tau. So this e is going to turn into e to the negative tau minus e to the negative 2 tau times g of t minus tau with respect to tau. And that should give us a complete solution. So we can say that this is going to be our solution to this initial value problem. And so that should solve this entire question. So comparing this with our answer choices, the answer to this question, I believe, is D. Yeah, the answer to this question is going to be D. I guess the only difference is that they put the G before our F thing, but it ends up being the same thing. So yeah, so I think at that point that solves this entire final. Nice. That was a pretty long one, but all right, cool, nice.